Are you still coding? Don't you know that the AI is taking over? You should just stop coding and surrender, right? No, we are not gonna give up. We are not gonna let the vibe coders win. In this video, we will learn about the concepts. We will learn about Rust, the most loved programming language by developers, and we'll go through all the chapters of the Rust by Examples website. This is a great opportunity to learn with a practical approach, so a very little theory and a lot of examples and code. This video is 3 hours long, so I don't expect you to finish in just one go, so I highly recommend you to subscribe and come back later. But now it's time to dive deep into the Rust world. Let's go! This is a complete Rust bootcamp in one go, and we will learn Rust by example. And this is not a random name I chose, but we are using the Rust by example site. What I'm doing is basically going through all the lessons here. We have many of them, and of course I'll try my best to enhance this very nice guide. It's a very practical approach, and instead of having a lot of theory, we'll just dive deep into the code. Even the first lesson is just a hello world. This is recommended for someone who wants a very practical approach, and it's not a problem for you to skip the theory just a little bit, and maybe you'll come back later to learn some main concepts. Rust in a practical way. Let's get started, no BS. Let's start with the hello world. We have this Rust code, and you should focus on these lines. In Rust we have functions defined with the fn keyword. Here we have the name of the function. Here we have the arguments. We have no arguments here. Comments with the double slash, nothing strange here. Something which might be a bit strange is that to print hello world, we have this println exclamation mark and then a string. And if I type here, display button, I should see the output. Let's see. Okay, hello world. This is how we will go through this whole bootcamp. We will read the text. I'll try to explain something to give some additional context, and then we'll just keep going. Okay, if you have any question, just drop them below for each section. All the sections will have timestamps, no problem. You see here, println is a macro. We will go back to macros later. For now, let's focus on a simple hello world. So this is how you make an hello world in Rust. Now, we can't see that in the browser, but this should be in a file with an rs extension. So for example, we imagine we created a file called hello.rs, and then using the Rust compiler, I can compile this file, okay? And then I can execute it. Since we are here, we are in the browser, we are skipping this, but they are telling us that this is how we should do this in our terminal or IDE, or maybe not, because we also have a package manager. But let's say that in my Rust hello world, I also go through this example. Something I really like about this course is that, of course, you can do some changes here. So for example, here instead of word, I can type hello Francesco, and then I play, and it actually executes this code. So this is also interactive. This is a very nice idea to make some modifications, so you can try it out by yourself. You can replace this with your name. Let's go to the next lesson. Comments. Okay, I'll go quick here. Double slash, single line, slash asterisk, ending with asterisk slash, to have comments on multiple lines. We also have the doc comments with triple slash, and we also can generate library docs for these enclosing items. Okay, here we have some examples. We already saw the comments in the previous lesson, and there is the link to the library documentation. If we hit play, we have another println. We also have a spoiler on how to declare a variable in Rust. Let x. We will go back to this soon. Formatted print. So this is interesting that they start right away with this on how to format the output. There are so many different options. We have this format exclamation mark to write a formatted text to string, print with exclamation mark, println to have a new line, it's similar to Python. We have eprint and eprintln to print in the standard error instead of the standard output. If you're familiar with JavaScript, this is probably not new. And here we have some examples. You see, you can also have these curly brackets and then the argument you want to print. If we try to run this very long text, also with some decorators, I would say, attributes, we have an error because on line 37, if we have two variables that we want to print, we need to actually provide two arguments. So for example, here I will add James. Let's see if this does work. And now I have all the prints here. Okay, there are so many examples here. I'll go fast. For now, I think with a println, you can focus on this example. Okay, on line 4, you can print something and then having the argument here. This, of course, can also be a variable. Sometimes it's hard in Rust to print, I don't know, an array or a vector, so we'll have to do something a bit different here. We'll have to add an attribute with the Derive debug, but we'll see this later. For now, for single variables, this usually works. When we want, for example, to format text for debugging purposes, probably we'll see something like this. Keep this in mind. It's curly brackets with a colon and question mark. I think in this case we don't have an example of this. No. We'll have it probably later. On line 43, we have this attribute, a loaded code. On line 43, we have this attribute, which is to disable a warning, because if in Rust, if we declare a struct, probably we want to use it. So the compiler might give a warning. Let's try to comment this real quick. No, we don't get the warning here in this output, but probably in a real IDE environment we will get this warning. Okay, let's go to the next lesson. Okay, debug. We have the lesson here. So all types which want to use std_fmt formatting trace require an implementation to be printable. All types can derive the fmt debug implementation. Let's see a practical example. We have a struct, for example, with this Derive debug. I think this can also be used with arrays, but now here is just using it for structs. For example, let's try to execute this one. We have a unit-like struct, this is called. We will hopefully see this later. We have this println with these curly brackets with colon and question mark. You see here we have 12 months in here. And then Christian later we have this println basically. The problem with Derive is there is no control over on how the result would look like. In this example, we'll have just this printed like this. Is this useful or not? It depends on our goal, of course. We also have a pretty print for the debug with this colon, hashtag symbol and the question mark. And in this case, we have a print which is hopefully easier to read. I don't use it often because usually I just want to have the results, but you can also use this one. Of course, you can implement your own FMT display to control what is shown here. And here we have a quick lesson about display. We can implement this manually and we can use these curly brackets as a print marker. Let's see an example here. We need to import this. We'll talk about modules later probably, but just to get used to the syntax here. Of course, here we have a practical approach, so we need to read something that we can't understand 100%. Then we can define a struct called structure in this case, and then we can use this curly brackets marker, implement this trait. We'll talk about traits later, they're similar to interfaces, and then we can implement manually this type. Here there is an implementation of this display, and FMT display is usually cleaner than FMT debug, but this can be a problem for the standard library. For example, we can have different types that hold this T. This is about generics. We'll also talk about generics later. Maybe we want to display them in different ways. And for all these generic containers, FMT debug debug must be used for these generic cases. Let's see it here. For example, we import this fmt. We have this derive debug annotation attribute. We have this struct. These are types. We'll talk about this soon. And then we implement this display for this min-max struct. Struct is how we define objects in Rust. This is how we define a function. This arrow is the return type, and here we have these arguments. Okay, don't worry if now you don't understand what these ampersands are. You can just identify here two arguments. One is just self and one is this formatter, and then we write these two arguments, self0 and self1. Then here we define a struct where the fields are nameable for a comparison, and then we can implement, for example, display for a 2D point here. We implement this display for point 2D, and probably we want this to be in X and Y coordinates. Let's see here the main function. We have this min-max struct instance, and then we use println to compare, for example, these structs. We have this, then we have display, and then we have debug here with curly brackets, and here curly brackets with colon and question mark. Then we have another println. We create an instance of this point, and then we try to print the compare points, display, and debug. Let's try to run this one. Let's see if we have an error or not. If we have an error, we will fix it, of course. This does work. We have the display and the debug. You see, they look a bit different. It depends what we want to do with them. For example, if we try to uncomment this and we try to run this one, we get an error because the binary with this B has to be implemented. So fmt display has been implemented, but fmt binary has not, and so it can't be used. We need to implement this binary to make it usable in our print. For example, for list, we can try to implement this display, but this might be a bit tricky because each write generates a different fmt result, and so we should be able to handle all the results. And this is why Rust provides this question mark operator. For example, we can use this question mark on write like this. Write f curly brackets value, and you can see here at the end this question mark. It tries to write to see if it has errors, otherwise it just continues, so at least it will not block our flow. And here we have an example of using this question mark in this write function. You see it's using it here, for example, in a list containing a vec, which is a vector. If you're not familiar with Rust, this syntax might be a bit confusing. We have a for loop, we have an if statement. We will have examples with all these syntax and constructs. Let's see how it looks. If we hit play here, this function main, we have this vector, and then when we print it, we have this 1, 2, 3. We can try changing the program so that the index of each element in the vector is also printed. Let's try it out. Something like this. Let's try it. 0, 1, B, count. Let's see. We should have a colon here, like this. Let's see. Okay, it's almost correct. I just have to invert count and V. Let's try again. I'm trying this with you, so this might be not perfect. It worked. It should remove the space if we want to get max grade. Let's go to the next lesson. Formatting. We have seen formatting, which is specified with a format string. We have these examples like this, with curly brackets, with X, which I think is hexadecimal, and other types. The same variable can be formatted differently depending on which argument type is used. For example, here we have a city with a name of type static string, a latitude and a longitude with F32. F stands for float here. And then we can implement the display for the city with a latitude and a longitude. We can add this grade symbol here. We also have colors here. This is another example. And then in the main function we have city and color. Let's see what's the output here. Okay, for example here for Dublin, Oslo and Vancouver we have the name, latitude and longitude. N stands for north and W for west. See here we have all the logic for how we want to display, for example, these cities. And for color, for example, I want to have red, green and blue with these three values. Okay, we also can view a full list of formatting traits. You can have a lot of fun here once you get into this rabbit hole, but let's go back to our lesson. Now let's start with primitive types. Okay, I think this part is very, very important. Rust provides access to many primitive types. There are some scalar types, signed integers, unsigned integers, floating point, a char, Unicode scalar value, a bool that can be true or false, not capital, and it also has this unit type whose only possible value is an empty tuple. Those are scalar types. There are also in Rust something called compound types, like arrays and tuples, and all the variables can be type annotated. Numbers can also have suffix, and usually we have some defaults. Usually the compiler can infer the type based on the type we assign when we declare a variable. Here we can define a boolean. This is a regular annotation. We can have this suffix annotation. Honestly, I never used this one. I prefer this one way more. If we don't use any annotation, like for example here, default float, and we assign a value 3.0, we will have an F32. If we type let default integer and then we assign just 7, that will be an I32 type. Something cool about Rust is that type can also be inferred from the context. If we initialize a variable, this mute stands for mutable, we will see this later, and we assign a value 12, so by default this should be an I32, but if on the next line we change the value to a very big number, the type will be inferred to be an I64. This is amazing. We can have a mutable variable that can be changed. Here, for example, let mutable equal 12 to 21. We can't change the type, so the mutability is just about the value and never about the type. We can't change the type of a mutable variable. But variables in Rust can be overwritten with something called shadowing. We can basically declare the same variable again with the same name in the same scope. Rust doesn't complain here. We can use this at our advantage or disadvantage. We need to know what we are doing when we are shadowing a variable. So basically declaring the same variable with the same name, some lines below. Here we have an example of an array like this. We can have this type and then the length of the type. We need to define how long this array is. And then here there is an example of a tuple. A tuple is a collection of values of different types. So we can have different types in a tuple. They are not key value pairs, but they are just some values that can be of different types. And here, for example, we define different types. We have a boolean and some numbers. Let's try to run this one. We have an error on line 17. It's complaining. Here we can't change the type to a boolean. Let's try again. We have basically no type because we are not printing these variables, but at least we don't have an error. So we fixed the error. Literals and operators. Types like integers, floats, characters, and strings, and booleans, and also the unit type, can be expressed using literals. For example, integers can be expressed using hexadecimal. You can also use an underscore to have a better visibility of big numbers. For example, 1000 can be also written like that. Rust also has support for the E notation. And of course, we need to tell the compiler which type of literal we want to use. Otherwise, the default one will be used. And here there are some examples with integer addition, integer subtraction, We can use the scientific notation, Boolean logic here with this one. It's similar to JavaScript. We can also have bitwise operations. Okay, let's try it out. I like this feature that we have at play here, and yes, we have the expected output, so we can play around with different literals, and also we'll introduce some operators here. And it's nice to know. I think tuples, they deserve a specific quick lesson. What is a tuple? A tuple is a collection of values that can have different types. It can also be the same type. How are they constructed? They use parentheses. We saw an example some minutes ago. Each tuple itself is a value with a type signature. T1, T2, different types. A great use case for tuples is that they can be used as a return type of function. We didn't introduce functions yet, but hopefully you have an idea of functions in programming. For example, here, let's try to understand this syntax here. Function reverse, we have a pair of an i32 and a boolean, and as a return type, we have a tuple that has a bool and then an i32. And here, for example, we define this variable of type tuple, and then we return, you see, we have int param, bool param, and we return bool param, int param. This is a trivial example, but it's just to understand that we can return multiple types easily with a tuple. Here, for example, we have a struct of a matrix, and here we have this long tuple with many different types, and values can be extracted from the tuple using the tuple indexing. I think we saw an example when we saw the formatting some minutes ago. So we can have .0, .1. Since in tuples we don't have key value pairs, the only way to understand which is the value inside of a tuple is by indexing. It starts from 0, and for example here, this is the index 0, index 1, and so on. The tuples are printable, so we can use this symbol with curly brackets and colon and question mark. Tuples that are too long cannot be printed. This is just so you know that. Here there is an example with this reverse function with this tuple, the example we saw here. So we reverse this i32 and boolean to a bool i32. We also have a print here. To create one element tuples, the comma is required to tell them apart from a literal surrounded by parentheses. For example, here we need to put this with a comma. And tuples can also be destructured to create some bindings. For example, here in this case, we have a tuple with 1, hello, 4.5, and true. And we can have a variable of type tuple, like ABCD, equal to this tuple. And then we can print it, for example, having all these 4 values. For example, here we have a matrix with 4 float values. And then we can print it. Let's try to run this piece of code. And here we have all the output. If you want, you can do these exercises. I will skip them because I want to keep going. Let's dedicate some time to arrays and slices. What is an array in Rust? An array is a collection of objects of the same type. In Rust, arrays are of the same type, and they are stored in contiguous spaces in memory. How are they created? They are created using these squared brackets, and you also need to know the length. So at compile time, we need to know the length of the array. This is why in the signature, we need to express the type of the array and the length of this array. Slices, on the other hand, they are similar to arrays, but we don't know the length at compile time. A slice is a 2-word object. The first word is a pointer, and the second word is the length of the slice. Slices can be used to borrow a section of an array, to get a section of an array. We'll talk about borrow and ownership later. They have this type signature, %t. For example, here we have a function that borrows a slice like this. You see the slice is the input, the argument, and then we print the first element, and you can also print how many elements this slice has with this method slice.len. Here we have a main function with a fixed size array with the type and the length here. We can also initialize all the elements with the same value, like this. The indexing, as it's usual in most programming languages, is that the first element of the array starts at the index 0. And we also have the len method that returns how many elements are in this array. Arrays are located on the stack. We will not focus on stack and heap here because we want to focus on the practical approach. And the arrays can be automatically borrowed as slices here. Slices can point to a section of an array. Here we can have a preview of how testing in Rust works. We'll probably have a separate section, but this is just to check that, for example, this empty array is equal logically to this ampersand and empty square brackets. Arrays can also be accessed using .get, which returns an option. Option is used in Rust to replace the concept of null. You might be surprised, but we don't have the null keyword in Rust. Instead, we have this option that can have two values, some or none. We also have a spoiler about this match statement. This is just to get used to the Rust syntax. Okay, so if you don't understand some of this syntax, is fine. Okay, we have a for loop and we are trying to get all the values inside this array. Let's try it out. Let's see if we return an error or not. No, we don't have any errors here. You see, this for loop will have this output. We are printing the I, which is the index, and the value. Okay, so what we did some minutes ago was useful. So now we should be able to understand, for example, this is basically this 5. And you see, we can handle, for example, if we don't have this index, we can return a print, let's say, hey, you are going too fast, the array ended, so we need to do something different. And here we have also all these prints of everything here. Let's dedicate now some time to custom types. Rust custom data types are formed using two keywords, struct, we already saw a couple of examples, and enum. Enums are very powerful in Rust. We can also have constants in Rust using the const and static keyword. Something very important before we proceed is that in Rust all the variables are immutable by default. Unless we explicitly use the mute keyword, they are already immutable, so even if we define a variable with let. And we'll see probably the differences between using const and let. Let's talk about structs in Rust. They are used to have something similar to objects. There is not a primitive concept of object in Rust, but this can be done with structs. There are 3 types. One is tuple structs, which are basically tuples with names. We have the classic C-like structs, and then unit structs, which are fieldless. They have no fields. I think we already saw an example some minutes ago. This is a simple struct. So this is a classic C-like struct with a name, and then we define the type, name and age, and age is an unsigned 8-bit integer. We can have this unit struct like this. Here is an example of a tuple struct pair. For example, a point, classic use case to have a tuple struct. For example, we want the x and y coordinates. Here it is. Here, for example, it defines the point with a classic C-like struct, but this can also be defined, for example, like this. Something powerful about structs is that they can be reused as fields for other structs. So, for example, we can have a struct rectangle that has a top left and a bottom right that are points. For example, in this case, we are using this one, the struct with 2 fields with a point. And then here we have some examples. Here we can define a new person with a name and age. We are using this one here. So we can define these 2 variables, and then we define a struct based on these 2 values. And then we can print it, of course. For being able to print it, we need to add this derive debug attribute. We can instantiate a new point here. For now, for point, we're using this type of struct, similar to the person one. It can access the field of the structs in this way, since structs they have names, key value pairs, we can access using the key. Struct points as key x and y. This is, for example, is not possible with tuples, so we have to use the index 0 and 1. Here we can access using the key. We can structure the point using the let binding like this, let point using this x and y left edge and top edge equal to the point we already have that defined here. We can define, for example, this rectangle. We can instantiate this unit struct, instantiate a tuple struct, and then we can access the fields of a tuple struct in the same way as we access the fields of a normal tuple, like this, with 0.0 and .1. We can also destructure a tuple struct like this, and at the end we can also print it. Let's try to print it out. There it is. Let's keep going. If you want, you can make a couple of examples, but let's keep going. Let's talk about enums. They allow the creation of a type that can be of different variants. Classic example, traffic light can be red, yellow, and green. Sometimes there are some variants depending on where do you live, but just to give an example. For example, a die can have a value from 1 to 6. Why enums? Enums are powerful because they are useful to avoid errors, identify different values for a variable, for example, and they are very useful so we are sure that the value will be just one of the existing value. For example, if we define a die that has the 1, 2, 3, 4, 5, 6 values, this die will never have the value 7. For example, here we have a web event. The page can be loaded, not loaded. We can have a key pressed, maybe we hit paste, maybe there is a click. The event is one of these. This is also useful, so we need to implement what happens, for example, for each of these events. And a great way to use this is to use this statement called match. It's like a switch on steroids. Based on this web event, we can have a match statement on this value of the enum, and here with this arrow, we can define what will be the output. In this case, we are just printing something, but think how powerful this might be. Here we could open curly brackets and actually execute some specific code based on this event. If we forget here to implement some of these use cases, also if we forget here to implement a specific case, the compiler starts yelling at us. So this is very useful. And here there is an example with a function main. We define different variables that are different web events. Let's try to run this one. And here we can see, for example, the output based on this match statement. Again, very similar to a switch. Type aliases. If you use a type alias, you can refer to each enum variant using this alias. And this might be useful, for example, if the enum's name is too long or hard to remember. Check this name here, very verbose enum of things to do with numbers. So we can create a type alias like this, and then we can just use operations instead of this very long one. This is especially useful, I don't know, for some legacy applications. So we don't want to touch this, but maybe we can create something which is easier to remember for us, and also less typing, which is also nice as developers, especially if you are lazy. We didn't introduce this impl keyword yet, but this is something that we might see often. In this case, we have the self alias. It basically replaces this very long name, and is also easy to remember and very easy to notice. We already saw the use keyword some minutes ago, but here now let's talk quickly about this use declaration. So we don't have to do some manual scoping. For example, here we have an enum for stage, an enum for role, and here we can use this create stage and create role. And now instead of using stage beginner, or similar to what we did before, like web event, colon, and the event type, it's basically an alias to have a shorter name. And of course, this is useful also when we want, for example, to import an external package. We are seeing this in the enum use case. Probably the use case of when we do this with an external crate, an external package. In Rust, crates are basically packages. It's basically more famous than what we see here. But since here we introduced the enums, we are seeing this use with enums. This is just a difference. If we see the previous example in the match statement, this switch statement, we had web event, colon, colon, and then click and something like that. Here we can just use beginner because we defined this use, create, stage, and so on. We can also have a use, create, role asterisk, and then we can just use something like this, so student and teacher. Enums can also be used as C-like enums, if you know C, of course. So we can have this enum, for example, for a number, can be 0, 1, or 2. It can also have an explicit discriminator, like red, green, and blue with the current value. And enums can also be cast as integers. Let's see the output here. 0 is 0, 1 is 1, roses are FF0000, violets are 0000FF. Common way to implement a linked list is using enums. For example, we have a list and a cons. Here the syntax can be a bit too advanced, but no worries. Cons is a tuple struct that wraps an element and a pointer. Think as this as a pointer to the next node. And nil, which is not a null keyword in Rust, but is something specific about this list, is just to identify the end of a linked list. You can implement this list. You can create a new empty list that has type list and it starts empty. And then we can consume this list and return the same list with a new element. For example, we can have this function prepend with this element U32, and then we return a list that has this element and then it points to itself. And then we can return the length of this list. I can say that this might be not super easy to understand. We also have this asterisk, which is the dereferencing operator. No worries, let's try to understand the basics here. This stringify returns a representation of the list, so it's basically a format as we did before, so basically we want to print this list. Here we have the main function. We can create this empty linked list and then we can prepend some elements, for example 1, 2, and 3. And then we can print this linked list with this length, and then we can try stringify method. Let's see the output. Not the easiest example ever, but this is an implementation of this linked list. So we have a list that has linked elements like this, 3, 2, 1, and then nil. We'll see box and methods. Constants in Rust. Rust has two different types of constants. One is with the const keyword and one is with the static keyword. Const is an unchangeable value and is the most common one. And static is a possible mutable variable. The lifetime, how much this does live in the scope, is inferred by the compiler and doesn't have to be specified. For example, we have this const i32 equal 10. Then we also have a static language. This is a string literal with a value Rust. We have a quick function here to define if something is big. For example, if we have a number which is bigger than 10, then it returns big, otherwise small. We can also see a ternary operator here in Rust, even if we didn't introduce the if else yet. If we try to run this code, we have an error because we tried to modify the value of this const. So this has to be commented out. And now we have, this is Rust, the threshold is 10, in this case 16 is big. Let's talk about variable bindings. Rust provides type safety with static typing, and this is great. I love this approach. Variable bindings can be type annotated when declared, but in most cases the compiler will be able to infer the type of the variable also from the context. So we don't have to annotate everything. Great plus when you use Rust. Values can be bound to variables using the let binding, the let keyword binding. We already saw let a couple of times. In this case, we are introducing it formally. For example, in this function main, we have 3 variables declared using the let keyword. We have an integer, a boolean, and a unit type. We can copy this integer inside another variable called copied integer. Then we print all these 3 values. The compiler in Rust is very annoying. If we declare a variable but we never use it, it will throw a warning. If we want to avoid the warning, we can use an underscore at the beginning of the name of this variable. So if we have something like this, we declare a variable but we never print it or use it in any ways, we should get a warning. Let's see if we get this warning in this browser compiler. We don't. The warnings may not be shown in this browser, but if you try to copy paste this on a real local IDE, you will have the warning for sure. Mutability. Variable bindings are immutable by default, but this can be overridden using the mute modifier. We already saw this some minutes ago. Here we are introducing this formally. We have this let keyword with a variable that also starts with an underscore, and then we define a variable which is mutable. Here this mut is the key here, and in this case we can change the value here. For example, we can add a 1. Rust supports this plus equal notation. What will be the output here? Let's see. Is an error because on line 13 we try to assign a new value to an immutable variable. The fact that we have a let here doesn't mean that this can be changed. This is different compared to JavaScript. Let's try again. And now it's happy because this mutable binding variable, we print 1 and then we print 2. Remember that we can change the value, but for example, we can't say something like this. We can't change the type. We should get an error here. We get an error. Expected due to this value, expected integer found bool. So even if the variable is mutable, we can't change the type. Let's talk about scope and shadowing. Shadowing is when we declare another variable with the same name after this has already been used. And what is a scope? For example, this one. We identify scopes in Rust with curly brackets. And for example, this is a block, this one, and this has a smaller scope because it's of course inside another scope, the scope of the main function. All the variable bindings are constrained to live in a specific block. And if we try to use, for example, this variable binding outside this scope, the compiler will complain because we can't use it outside this scope. It doesn't know what this does mean. If we try to run this code, we get an error. We basically need to comment this line. For example, here in the outer scope, we have also this long-lived binding here on line 3, and then we print it on line 18, which is outside this inner scope. Let's see. And now it works. Variable shadowing is allowed. We can have this variable called shadowed binding equal 1. Inside this scope, we name it again shadowed binding equal ABC, and outside we shadow again in the same scope. So here we are shadowing in an inner scope, here we are shadowing this variable in the same scope. Let's try to run this one. So we have this print before being shadowed 1, in the inner scope is ABC. Here on line 12 we still have the value 1 because we are in an outer scope, and then we shadow this again later on line 15 and then 16. Of course, if we use shadowing we should know what we are doing, otherwise we will have some type of errors. In Rust it's important that variables are declared first. It's possible, not recommended, but possible to declare a variable bindings first and then initialize them later, but all the variable bindings must be initialized before they are used. For example, here we define a variable without initializing them. We define another variable inside this inner scope, and then we initialize the binding for the outer variable here. Outside the scope we try to print it, and then we define another variable. Let's see what happens here. We have an error because we try to print this another binding variable, but this has never been initialized. If we comment out this one, now we should be able to see it. Freezing. When data is bound by the same name immutably, it also freezes. Frozen data can't be modified until the immutable binding goes out of scope. we have a mutable variable here with this value. We are using the suffix type, personally not a fan, but it's okay. And then we try to type let mutable integer equal mutable integer inside this inner scope, but this is not mutable. And we try to mutate the value here. This is not possible. If we try to execute this one, we get an error. Comment this out. No output, but okay. If you're using shadowing, but the new variable is not mutable, it freezes. This is of course to avoid unwanted errors. Now, let's talk about types. Rust provides several mechanisms to change or define the type of primitive and types defined by the user. We'll talk about casting, specifying the desired type of literals, using type inference and aliases. Let's start. Casting. What is casting? Casting is conversion between primitive types. Rust doesn't provide an implicit type conversion, but of course we can do the explicit type conversion, also called casting, using this as keyword. The rules for converting between different types, integral types, follow the conventions of the C programming language, but not where C has an undefined behavior. We don't want undefined behaviors here. All the behavior of all the cast between integral types is very well defined in Rust. For example, here we have a decimal like this. We are also using this literal, and we can have this explicit conversion. We should get an error here. This is a very long text. Okay, this is not possible. Let's comment this out. We can have an explicit conversion. So this is allowed. What we do on line 8 is not allowed. Let integer equal decimal as U8 or character integer as char. If we try to run this, we should still get an error because of course we can't cast a decimal to a char. It doesn't make sense. Let's try it out. See if we still get some errors. No, all the errors are fixed, and here there are many examples on how we can do a casting between different integers. The important thing to remember here is that we use the S keyword. There are many examples. We also have this unsafe. This is something we probably will mention at the end of this video. Let's keep talking about literals. Numeric literals can be type annotated by adding the type as a suffix. For example, here we can define this x equal 1 u8 or y2 u32. These are called suffixed literals. This is when the types are known at initialization. If we define a literal without a suffix like this, the type, the default type will be used. Also, it will depend on how they are used. Let's say that we have let I equal 1, or we have let mutable I equal 1, and then we want to change this value to 1,000,000, then the type will be inferred by the compiler. We can use this function std mem size of val to understand which is the size of this variable in bytes. For example, here we have x 1 byte and so on, 4, 4, 4 and 8. F is 8 because is a float. Inference. The type inference engine is pretty smart, okay? It does more than looking at the type of the value expression during an initialization. It also looks at how the variable is used afterwards to inference its type, so it's also based on the context. For example, we define an element as an unsigned 8, then we define a mutable vector like this. We'll probably introduce vectors later, they are similar to arrays, and at this point the compiler doesn't know what type this vector has in. But if we type vec.push lm, the compiler understands that this is a vector of u8 integers. Pretty smart. Let's try it out. Yes, it doesn't complain. Aliasing. We already introduced the type statement, but let's make one more example. It can be used to give a new name to an existing type. The types should have these upper camel case names, or the compiler will keep complaining. The only exception is when we use usize or f32 or something like that. For example, we can have a type nanosecond, inch, or U64, with capital U here. It's important to remember that type aliases, they don't provide an extra type safety or an extra safety level. They are not new types. They are just a different name for the same type. This is important to remember. If you execute it, yes, we have something like this. Okay, this is just another quick refresher on aliases. Conversion. Primitive types can be converted to each other through casting. Rust allows conversion between custom types, for example struct and enums, using traits. Usually we use these from and into traits. Let's see an example. I think it's easier. The from and into traits are linked because usually if you can convert A to B, then you can convert B to A. So the from trait allows for a type to define how to create itself from another type. And we already saw this string from. So we can create a string using this string from method. We can convert, for example, this str, which is not the same in Rust as a string. We'll probably have a separate lesson on this. And for example, we can do a conversion of our own type. For example, like this, we use this convert from, we define this struct number with a value i32, and then we can do a from i32 for number, and then we convert this to this custom number. Let's try it out. We have this one. Into is the reciprocal of the from trait. It defines how to convert a type into another type, hence the name. For example, here we have this impl into number for i32, and then we have this function into self that returns a number. So for example, here we return a self. It's basically the reciprocal. And here in the function main, we have let int equal 5, and then num is of type number, which is int.into. Now, these examples are probably trivial and they doesn't look that smart. These are just examples to understand that we can have custom casting in Rust. And they are interchangeable. For example, here we have a from, but then we can use into. Let's try. It just works because we define the from, so now we have also into. Similar to from and intro, we also have TryFrom and TryIntro that are some generic traits to try to convert between types. The difference between TryFrom and from is that the trait TryFrom can fail, which is good. So we can, for example, return I can't convert that type. And we need, for example, to implement this TryFrom for this even number, and we see we return here if the value is basically a real even number, we return okay, otherwise we return an error. This is a syntax that you should get used as soon as possible in Rust. We can have a result that can return okay with an actual value or error with the error. With the excuse of this TryFrom, we also introduced the result construct. We also have some tests here. Let's try it out. We have no output here, but it's okay. It didn't give errors. If we try to change this, for example, we have an error. These tests, they were all good. I introduced a bug here. To and from strings. Converting to string. To convert any type to a string is very simple because we can just use the toString trait. It's similar to Java. Instead of doing just directly, we need to implement the fmt display trait, which automatically provides toString and also allows printing this type as we did at the beginning of this video. So we have, for example, this struct circle with a radius, and then we implement this display trait in this way, and we just return right circle of radius with the radius. Let's try to run this one. Circle of radius 6. This is how we can easily implement this trait. Sometimes it's useful to parse a string, and to do this usually we use the parse function. And for example, here we are doing this on the string 5. We can also specify a specific type we want this to be parsed in. To obtain this functionality on a user-defined type, we can just implement the from str trait for that specific type. I want to run this one quickly. it worked, so it actually did the sum of these two strings after parsing them, of course. And here we have a circle radius 3. We parsed this one, which was also very bad formatted, okay? What is an expression? A Rust program is made by a series of statements, like this one. In a function we have multiple statements. What kind of statements can we have in Rust? The most common two are declaring a variable and using a semicolon with an expression, like this. Blocks are also expressions with curly brackets, so they can be used as values in assignments. This is very important. The last expression in the block will be assigned to the place expression, such as a local variable. If the last expression of the block ends with a semicolon, the return value will be this empty type. Let's try this out. And we have here these three print statements. Now let's talk about flow of control. Sometimes we need to define which part of the code will be executed compared to another. Classical example is an if-else. Sometimes we want to execute a specific part of the code instead of another one. Or maybe we want to execute a specific part, I don't know, 10 times. Okay, this is basic concept. This is not just for Rust, of course, but we will talk here about flow of control in Rust, and also let's see if we have something specific and peculiar of Rust. Classic if-else statement, it's very similar to other programming languages. In Rust you don't need to surround the Boolean condition in parentheses, and each condition is followed by a block. For example, this is valid. The if-else conditionals are expressions, and all branches must return the same type. We have here, for example, definition of a variable n equal 5, and if n is lesser than 0, we print is negative, is greater than 0 is positive, otherwise print is 0. Pretty basic stuff. We can also have multiple conditions. This means and, so both of the conditions must be fulfilled to execute this part of code. Otherwise, we'll have this one. Let's try to execute it. 5 is positive, is a small number, because the big number is 10 here. And then we increase it by 10 times. We are executing, for example, this piece of code. Let's talk about loops. Something that I really like about Rust is that it has a loop called loop, which is basically a while true statement. Spoiler. Rust provides this loop keyword, and this is basically an infinite loop. If we don't have a break condition, like we have, for example, here, or an exit condition, it will just keep running forever. It's a nice idea to have a way for this loop to end. And it also supports the continue keyword, that just means start over again with another cycle. Okay, let's try 1, 2, 3, 4, 5. If count is specifically 3, it just prints the 3 word instead of the 3 number. Okay, that's enough, like it says here at the end. It's possible to break or continue other loops when we have to do with nested loops. Nested loop, it means that we have a loop inside another loop. In this case, the loops must be annotated with some sort of label. For example, here we have outer loop and inner loop. Otherwise, the compiler might not know what we want to break. For example, if we want to break the outer loop inside this inner loop, we need to have this label. Inside this inner loop, we can still break just the outer one. Let's see, entered outer loop, in the inner loop, break. This point basically will never be reached because it is outside the inner loop, but with this break it just exits the outer loop, so then we'll print just this one. One of the great uses of a loop is, for example, to try something indefinitely, an infinite amount of times, until the memory allows this to us, of course. If the operation returns a value, you might need to pass it to the rest of the code. So, for example, here, after the break statement, we can just type what we want to return. Here we will return, if the counter is equal to 10, we'll return the counter multiplied 2. So in this case, basically we are returning 20. We also have a sort of test here, assert. No output, but it's not complaining. Okay, if I put 10 here, we should get an error. because here we are returning 20. On the left we have 20. While keyword, this is famous also in other programming languages, here we have an implementation of the famous feeds buzz game. This is probably a game you know, otherwise you can click here. Group word game for children to teach about division. If you have a number which is divisible by 3, you should say feeds. If it's divisible by 5, you should say buzz. If it's divisible by 3 and 5, you should say feeds buzz. And this is an implementation, for example, of this simple game. We also know an alcoholic version of this game. 1, 2 feeds, 4 buzz, feeds 7, 8 feeds buzz 11. After a couple of beers, this probably becomes harder to play. For loops, we have the for in constructor that can be used to iterate through an iterator. One of the easiest way to create an iterator is to use the range notation, which is a dot b. Let's see this in this example. For n in 1.101, and this is basically the same implementation of the feeds buzz game. If we want to include the last value, we can add an equal here, 1.101 or 1 ... equal 100. This will take 100 both here and here. Let's try it out. It ends with feeds buzz. It ends with feeds buzz. The for in construct is able to interact with an iterator in several ways. Depending on the iterator we use, we'll have different behaviors. We have the iter that pours each element of the collection through each iteration. We have into iter that consumes the collection. We have iter mute that mutably borrows. We will see mutability and borrowing later, allowing the collection to be modified in place. To understand the difference here, you should check the type of each match branch possibility. It's like a case in a switch. So for example, here we have this as a match, we have it in this way. Here we have just like this, and here we have at mute. We basically already introduced the match statement, but now let's do this formally. Rust provides this very powerful pattern matching using this match keyword. It's probably my favorite construct in Rust. What I really like about the match statement is that all the values must be covered. For example, let's say that we have a number here. Then maybe we want to return something about this number. We need to explicitly say what should happen for each of these numbers. For example, 1, 2, 3, 5, 7, 11 is a prime, 13, 19, you are a teen. Otherwise, nothing special. So this is important because we can handle all the rest of the cases. It's similar to the default keyword in a switch statement, but we still need to handle this one. If we forget, for example, to add this one, the compiler will start complaining. Let's say, for example, that we have a boolean and we implement just what will happen when the boolean is false. We have no implementation for where the boolean is true. In this case, the match statement will raise an error. One great plus of the match statement is that it forces us to cover all the possible values of this variable. Of course, here is trivial, but I think in a huge code base, we need to be sure that will happen something when this boolean is true or false, and maybe we forgot one implementation. It's true. If we type false, should have false. Yes, a match can destructure items in different ways. Tuples, arrays and slices, enums, pointers, and structures. For example, tuples can be destructured in a match like this. We define a tuple, in this case it's a triple because it has 3 values. It can destructure the second and third element, or like this one, or this one. So it's very powerful. Tuples plus matches is a great combo. Let's see the output. Great. Arrays and slices can also be destructured in a very similar way. We can have a match statement on the array like this, and then we bind the second and third element to these variables, second and third. We can ignore single values using the underscore like this. This is very powerful. We can also combine all these patterns. You can also bind some and ignore the rest. Great. We can destruct enums. For example, here we have an enum for colors. And in this main function, we can have this match that based on the color the destructor is using this match statement. This is very powerful. Let's try to execute it. It basically tries different variants for color, and once it finds it, it tells you what color is this one in different formats. Let's talk about pointers, and it's important to understand that we need to make a distinction between the structuring and the referencing. They are different concepts. With the reference using the asterisk, we saw a single example some minutes ago. And then we can also destructure using a different syntax like this. For example, here we have a main function. Let's say that we have this variable and is equal to a reference to 4. It can also be a reference to another variable, of course. Then we can use a match on this reference and return the @val. Prints got a value via destructuring and then the value. You can also dereference before the match. We have match asterisk reference and val, which is println got a value via the referencing colon question mark. If you don't start with a reference, because the right side was already a reference, like in this case, let not a reference equal 3, we can use ref, the keyword ref, for these purposes, that modifies the assignment so that a reference is created for this specific element. And then we assign this reference, like this. References can be retrieved using ref and also ref mute here. Ref as for the reference and also ref mute, like this. We can also destructure a struct like this. We define a struct here. This is the C-like struct. We can try to change the value here. And then we have a match statement with this variable foo. And based on what we have, we can execute different parts of code. In this case, it's just a print statement. Of course, you don't need a match block to destructure a struct like we did before. We can also have something like this equal to, for example, another variable like FAA. Here the match statement is just to handle different cases depending on the content of the struct. So it's basically destructuring it to understand what is the right matching for this specific struct. Destructuring also works with nested structs. Guards. A match guard can be added to filter an arm of a match statement, and this guard is basically implemented with an if statement. For example, some of these arms of a match statement, they have an if condition. Of course, the compiler won't take guard conditions into account when it checks if all the patterns are covered. In this case, we are basically handling all the cases manually. If we access a variable indirectly, this makes it impossible to branch and use that variable without binding again. And the match statement provides this @ symbol for binding values to specific names. For example, we have a function, age, that returns a number, in this case 15, and in this case we have a match on this function that returns 15, it will go on this one. And so it gets I am a teen of age 15. You can also use binding to the structure enum variants, for example, the option 1. For example, we have this sum number that returns an option with a sum, and here in the match statement we can have a sum with a specific value or another type of sum with an n with a different value. In this case, the answer is 42. If we try to change this, it says not interesting. We went on a different value beside this sum of the result. I know that the match statement is powerful, but sometimes maybe we don't have so many cases. We just have 1 or 2 options. In this case, we can use something a bit different. For example, here we have an optional and we have just sum and underscore. Here, using the match statement seems a bit of an overkill. We can use just the if let construct. If let sum, we do something. Otherwise, we don't. If we see a match statement that has just one branch and an underscore, which is basically for everything else, and this is also empty, probably what we want is to have an if-let statement. The if-let statement can also be used to match an enum value, like we have here. You have an enum foo with bar, buds, and quotes with u32. Enums can have also different types, and in this case we can create example variables, and we can use the if-let keyword. If let foo bar equal a, we do something. In this case we just print it. Another benefit is that if-let allows us to match, not the keyword, just to match enum variants without a parameter. For example, here we have a compile error. Let's get the suggestion of the compiler. And we fixed it, adding this derive partial ick. That was easy because the compiler in Rust is usually very precise. There is a sort of new construct stable since Rust 1.65, which is let-else. Let-else is a refutable pattern that can match and bind variables in the surrounding scope like a normal let. Or it can also diverge when the pattern doesn't match. Let's see an example. We have a function here, and here you can see we have let, some count str, some item, equal it next, else we panic. We have also a way to handle things when the pattern doesn't match. The scope of name bindings is the main thing, the most important thing that makes the difference between a match and an if-let else expression. As you can see, this syntax is a bit confusing using the match statement in this way. We can also use while let instead of a match statement. For example, if we have something like this, with a loop statement, and inside this we have this match 1, we can make it more readable if we type something like this. Instead of having this loop match, we can replace it with while let. I like this syntax way more compared to this one. Yes, it works. Now let's introduce functions in a formal way. We already saw functions fn keyword since the beginning of this video, but now let's introduce them in a formal way. So functions are declared using the fn keyword. All the arguments are type annotated, so we need to add the annotation of the type here. If the function returns a value, we also need to specify the type after this arrow. We can also return multiple types. And the final expression of the function will be used as a return value. We can also use the return statement in case, for example, we return earlier. Usually, we don't need to explicitly use the return keyword in Rust because that's the default. The default is that the last statement will be used as a return 1. We have again the implementation of the feeds buds game here. But let's focus on the syntax. We have a function with the name of the function, the arguments with the annotation of the types, and the return type. And we will return this. The return keyword is not necessary here. If a function doesn't return a value, it will return the unit type parenthesis. And if a function turns parenthesis, so basically it doesn't return anything useful, we can also omit the return type, so we can omit the arrow with the return type. Associated functions and methods. Sometimes we have functions that are connected to a specific type. For example, when we have structs, we can have associated functions and methods. The associated functions are functions defined on a type, and methods are associated functions called on a specific instance of a type. For example, here we have a struct point with this implementation block. For example, this origin is an associated function because it's associated to this specific type, which is point in this case. Associated function here, it also can take 2 arguments. In this case, we have instead a method for this struct. like this. And we have this @self argument that is the short for self @self, where self is the type of the color object. And we can have here different methods like this one. For example, this one requires the color object to be mutable. We have a function translate, and this requires the object to be mutable, otherwise it will throw an error. We have other examples. We have an error, for example, if the rectangle is immutable but the method requires a mutable object, and so on. So this is the basic definition and difference between associated functions and methods. Let's talk about closures. Closures are functions that can capture the enclosing environment. We'll see an example, of course. And this is the syntax. It's a bit weird, but this is the syntax of closures in Rust. Closures are very convenient when we need something on the fly. And calling a closure is exactly as calling a function, and the input variable names must be specified. About the syntax, we use the double pipe instead of the parentheses. We can have an optional body delimitation for a single line expression. Of course, otherwise it's mandatory, of course. It has the ability to capture the outer environment variable. Let's see an example. We have this outer variable here, and then we can define this closure annotated with this i32 that returns an i32, and here you see we can use this outer variable. This is usually not possible for a function, and in this case we have the closure inferred. We don't have to specify types, so for functions we need to specify the type in the arguments and in the return type. Closures can also be inferred. Okay, so this is for the lazy developers. How can we call a closure? Like this, the same as functions. For example, if we want a closure that just takes no arguments and returns a specific i32, we can define this like this. We'll run this 43, 43 and 1, because here we are adding 1 to the outer variable. Capturing. Closures are inherently flexible and will do what the functionality requires to make the closure work without the annotation. Closure can capture variables in 3 ways: by reference, by mutable reference, and by value. Here is the syntax. The default is by reference, so using this @t. Let's see an example here. We have color, and we have a closure to print color that borrows color and stores the borrows, and then it prints the variable. And then, for example, we can call this closure like this. And here, for example, color can be borrowed immutably again from another variable, because the closure only holds an immutable reference to this color. We can have a closure that increments a count like this. Let mute inc with double pipe count plus equal 1, and then we print it. And then we can call the closure using a mutable borrow like this. If we try to reborrow, we will have an error here. We can have a consume closure that prints a movable variable, like in this case. And then we can call it. Let's try to execute this. We should get an error. No. Because it was already commented. So if we try like this, then we should get the error. If we use move before these vertical pipes for the closure, this forces the closure to take ownership of the captured variable. So we didn't talk about ownership yet. We can also use move before vertical pipes to force the closure to take ownership of a captured variable like this. Let's try it out. True and false. As input parameters, while Rust chooses how to capture variable on the fly, without any type annotation, this is usually not allowed when we write functions. When we have a closure as an input parameter, the closure complete type must be annotated using some traits that depends on the behavior of the closure. We have fn, fn mute, fn once. Fn is when the closure uses the captured value by reference at t. Fn mute stands for mutable, is when the closure uses the captured value by mutable reference at mute t. Fn once is when the closure uses the captured value by value, so just t without the reference. The compiler will try its best to capture variable in the least restrictive manner possible. Let's see some examples here. We have this function apply, which is a function that takes a closure as an argument and then calls it, like this. This is a function that takes a closure as an argument and calls it. Then we have a function that takes a closure and returns an i32. In the first case we have fn once, and in the second case we have an fn also with the type i32. And in this function main we define a couple of variables. Here we also add the toOwned that creates some owned data from a borrowed one. And in this case we capture two variables, greeting by reference and farewell by value. So the first one requires fn, but the mutation here of the farewell forces fn mute to be used. And we can also manually call this drop method. We can then call the function that applies this closure, apply to diary, like this. Let's try it out. I said hello, then I screamed goodbye, now I can sleep. 366. Okay, it's a strange diary, but this is just to have an example, to have closures as input parameters in functions. Type anonymity. So closures, they capture variables from the enclosing scope. And this of course has a consequence. We haven't introduced generics yet. This is a concept not just by Rust but for many programming languages. Let's see this example. We have this function apply, which is of a generic type. When a closure is defined, the compiler implicitly creates a new anonymous structure to store this captured variable. And in the meanwhile, it implements one of the traits, fn, fnmute, and fn_once, for this type that is still unknown. The type is assigned to a variable and it will be stored until it's called. And since this new type is of a type which is unknown, any function will require to use generics. We still need to bound one of the traits, fn, fnmute, or fn_once. For example, here we added fn, capture x into an anonymous type and implement fn for it, like this. For example, if we try to run this one, we have 7. Input functions. Closures can be used as arguments, but can be functions and be used as input? The answer is yes. You can declare a function that takes a closure as a parameter, and any function that satisfies the trait bound can be passed as a parameter. So we can have a function, for example here, that takes a generic f argument, then we define a wrapper function satisfying this fn bound, then we define a closure that satisfies the fn bound. Fn, fnmute, and fn_once traits, they dictate how a closure captures the variables from all the surrounding and enclosing scope. I'm a closure, I am a function. Closures can also be used as output parameters, but anonymous closure types are anonymous and unknown by definition, so we need to use the impl trait to be able to return them. The valid traits are fn, fnmute, and fn_once. We must use the move keyword that says that all captures will occur by value. An example, we have a function and then returns impl fn, like this. Here impl fnmute, impl fn_once. So it can also be used as a return type. Now let's see some examples of using closures from the standard library. Iterator any is a function that when is passed to an iterator will return true if any element satisfies the predicate. Otherwise it will return false. This is the signature. And here is an example on how we can use it. We have a function main, we define two vectors, and then we use this .iter and .into iter. The first one yields an ampersand i32, and the second one yields an i32, so there is not destructuring in the second one, and in the first one there is a destructure. Let's see. We also have an example here with arrays, array1 and array2, with a similar implementation here. For example, into iter moves vec and the elements, so they can't be used again after. If you try to use them, we'll have an error. We can search using iterators, using iterator find, which is a function that iterates over an iterator and try to search for the first values that satisfies some condition. If it can find any value that satisfies the condition, it will return none. This is the signature, and here again is an example. We have two vectors. We define a variable which is mutable with vec1.iter, mutable to iter with vec2.intoIter. It's similar to the previous one, and it will try to find something, for example, to find 2 inside the first vector and 2 on the second vector. So probably will return something on the first one and nothing on the second one. Some, 2, and none. Some, 2, and none. It's similar syntax. The first one is a vector, the second one is an array. What if you want to find the index of the item? You need to use iterator position, this one. Let's see here. You see dot position here. And here the index is sum 5, 0, 1, 2, 3, 4, 5. Higher order functions. Rust provides a higher order functions that are functions that take one or more functions and they produce a function which is hopefully more useful. Let's see an implementation. We have this function is odd that returns a boolean, and then we have this function main, and inside this we are using the is odd function inside this for loop. We can also have a more functional approach. Let's try it out. It finds the sum of all the numbers with odd squares under 1000. Imperative style and functional style. Once you get used to probably the functional style, it's more compact and also less readable, of course. Diverging functions. Diverging functions are functions that never return. And they are usually marked using this exclamation mark, which is an empty type. So they have this syntax. fn foo returns an exclamation mark, and then we use this panic. So we intentionally panic. This function can't be instantiated because the set of all possible values this type can have is empty, which is an exact possible and empty value. It's a bit different. For example, here we have this function, sum function, and then we have this main function with this value equal to sum fn. In this case, this function returns. The program still keeps going. In this case, we should be able to see this print statement. But in this case, it's a different story. This code never returns, so in this case I will never see this line. This seems a bit weird, but it can also be useful. It can be cast to other types. This makes it flexible in some situation where we have an exact type, for example, in some branch and possibilities in a match statement. And this flexibility allows us to write a code like this. We have a function. Let's try it out. And we can have the sum of all the odd numbers up to 9. Now, let's talk about modules. Because usually in a Rust project we don't have a single file. So Rust provides a very powerful and great way to structure our project. The first part, which is very important, is the visibility. So which is the default visibility in Rust? Of course, it's the private visibility. By default, nothing is public and open in Rust. Of course, this can be overridden with the pub modifier, and only the public items can be accessed from the outside. So for example, inside this module called myMod, we have some private function without a modifier, and then we have these functions that are public. They can be used from the outside. Pub. We can also have a public module, of course. We can also have a private module inside a public one inside a private one, and so on. And inside this main function, we simulate, still in a single file, all these modules by using this syntax. And also here were all the errors in case we are trying to access something which is private. Okay, let's go quick here. Visibility of structs. Structs have an extra level of visibility because structs, they also have fields. Can we have a struct that has some fields public and some fields which are not? Yes, we can. The default is of course private. They can be overridden using the pub modifier. This is very powerful. Let's try it out. Open box. Yes, this was an example on how we can use it. For example, this was a public struct. And now they use declaration. We probably saw this at the beginning of the video. Now let's introduce this formally. So the use declaration can be used to bind a full path for a new name. So it can also be used for modules. It's usually used like this. We use a specific crate and then we can define some functions that we want to import in this new file, new part of the project. We can also use the as keyword to import them as a different name. I think it's similar to Python. So import this as other function. And then in this function name, then we can use this sort of alias that we used for this long import. Let's try it out. And yes, we are basically using this external crate. Super and self are keywords used in the path to remove ambiguity and when we are not sure if you're accessing some items or not. And they are also used to prevent some hard coding and maybe that we need to add an hard-coded path. For example, we have this function, we have a module with a public function inside it. And here, for example, we are using self for the function. We have a function called function, okay, and here we have self for function and super for function. The super keyword refers to the parent scope, of course, similar to Java and other programming languages, and the self keyword refers to the current module scope. Of course, also modules, they are nested in different scopes. Project in Rust probably has multiple files, many files. They can be mapped in a file directory hierarchy. For example, if we have something like this, we can have this split.rs file that has the declaration of a module, and a function, and a main. Then we have a my.rs file, is at the same level as a split. A module which is inaccessible, is basically private. And then it has a public module nested here. And then in my, there are two more files, inaccessible and nested. The nested one is public, with a public function and a private function. And the inaccessible one is public, and this is basically used to structure our code. The important part here is to understand that a module is private by default, and then the module or some functions can be defined as public. Crate. What is a crate? I think I already mentioned a couple of times this word. A crate is basically a package, and it has some files, it has some mod declarations. It's basically a single package that has some reasons to exist because maybe it solves a problem. Modules are not enough to be compiled. They need to be inside a crate. There are some crates that are a single module, but we really need a crate. A crate can be compiled into a binary or into a library. By default, RAII will produce a binary. This can be overridden by passing the -- crate type flag lib. How can we create a library in Rust? Here there is an example. We have a file. We can do something like this to compile it as a library, and usually they are prefixed with lib. This behavior, of course, can be overwritten. Using a library to link a crate to this new library, we might use this RAII extern flag. Everything will be imported under a module name the same as the library. What is Cargo? I think I already mentioned this a couple of times, but Cargo is the official Rust package manager tool. It's used to create projects, build projects, handle dependencies, unit test benchmarks. It's a whole complete and full-fledged tool. I think more programming languages should have something like Cargo. It's basically an all-in dependency management, package manager, unit tester, and so on. Huge fan of Cargo. You can go on crates.io to basically find some packages. At this moment, we have almost 130 billion downloads of crates. This is similar to npm in JavaScript. Dependencies. Most programs, they have dependencies on some other packages, other libraries, and Rust is not an exception. Technically, we might do this manually, just downloading files and put them into our system, but usually this is not the best option. We can use cargo to manage dependencies in a project. We can create a new binary project using cargo and typing the command cargo new and the name of the project, or if we want a library, cargo new --lib and the name of the library. If we create a binary, we will have a main.rs file. If we create a library, we will have a lib.rs file, but the structure is very similar. Cargo also creates a cargo.toml file. TOML stands for Tom's Obvious Markup Language. It's very similar to package.json if you are a JavaScript developer, and it's basically the config file for cargo that has the name of the package, all the dependencies, and to be honest, it's very straightforward, and I really love the approach of a .toml file. We have the name, version, the authors, and all the dependencies. And to add a dependency, there are different ways. One is to type cargo add and the name of the dependency. Usually in Rust, we just paste manually the dependency we want editing this file, which is also an option. We can also get dependencies from an online repository or from a path in the local system. And to build a project, we can just execute cargo build. We can also type the famous cargo run, which is a great way to test things locally and see if they will work or not, and if we will have some compiler errors. What is a convention? Let's talk about conventions. We saw this hierarchy with foo, cargo.toml, src, which stands for source folder, and main.rs. Let's say that we want two binaries in this project. What's the best way to achieve that? In cargo, the default binary name is main. Main is a bit special as a file name, but you can also add some additional binaries. You just have to put them inside a bin/directory. We can also tell cargo to just compile some parts and not all the packages or all the dependencies. So you can type cargo and then the side of the package. For example, in this case, we just compile the myother_bin.rs file and package. Cargo also supports benchmarks, tests, examples, testing. For many programming languages, testing is a nightmare. We need to install an additional package, then we have a library, then we need to choose which library is the best one to start with. It's usually like a very painful process. In Rust, this is, I would say, almost comfortable for being testing, because Rust supports unit and integration testing almost out of the box. A great way to get started is to create a tests folder, and inside that we can write all the tests. And how can we run this test? Cargo test will run all the tests that are inside this tests folder. And of course, you can run tests on specific files, specific functions. We will not go into the details in this video, but you can test specific parts of our project. And of course, you need to be careful to don't override and run multiple tests that can overlap concurrently. Single folder tests, we can type cargo test all the tests, or single test. This also supports pattern matching, can run some tests on some specific files that have some specific names. This probably will require an additional video. This is just to get started, let's say, with tests. Now, let's say that we want to build a script in Rust, because sometimes we might need a custom solution. We can add a build script like this, build equal and then build.rs file. But cargo will look for a build.rs file in the project directory by default anyway. We can specify environment variables, so this is just to get started and to know that you can have a custom script by having this build.rs file. Let's talk about attributes in Rust. We've seen this almost since the beginning. What is an attribute in Rust? It's a metadata that is applied to some module, a crate, or a specific item. It can be used for many different use cases. An example to disable warnings. I use this a lot. And usually they look like this. And this usually is applied to the item immediately following. For example, we use the Derive debug to print a struct. They can take arguments with different syntaxes, attribute key, attribute value. The important part is that when we see something like this, it means that we want a specific behavior on the item which is immediately below. Sometimes I call them decorators because this is how you call them in Java. The correct name for Rust is attributes. A classic one is the allow dead code one, to basically disable the lint and the warnings in the code. This is also useful for me during tutorials when, for example, I don't want to annoy you with all the warnings that the compiler can throw me, but I just want to focus on the output of a function. Sometimes I use it, consider this useful, maybe not for the production ready code, but while you are writing code if you have too many warnings. Another important attribute is crate type that can be used to tell the compiler whether a crate is a binary or a library. So now we are sure this is a library or a binary. It's useful. I honestly didn't use it much. Usually I know if I'm working with a library or a binary, but maybe for big code bases this can be useful. And in this case we don't need, for example, to pass the flag -- crate type anymore, because then Rust can understand automatically if that's a binary or a library. Let's talk about a CFG, which of course stands for configuration. These are configuration conditional checks possible through two different operators: the CFG attribute and the CFG macro for Boolean expressions. We'll talk about macros. The CFG attribute enables conditional compilation, and the CFG with exclamation mark evaluates to true or false literal, allowing for checks at runtime. For example, let's say that we want a function that only gets compiled if the target operating system is Linux. Can we do that? Yes. CFG target operating system equal Linux. This is useful and it helps us to create something which can be specific to an operating system, specific to an architecture, and so on. This allows us to really work on different platforms with the same code base. There are some conditionals like the operating system that are implicitly provided by Rust. But let's say that we want a custom condition. In this case, we can have something like this, CFG, and then we can write the condition here. We can try to run this to see what happens. Let's see. Here in the browser, I can't simulate this behavior, so I get an error, but if you try to have this on a local project and you try to run this Rust C CFG some condition, and then we'll probably have this message as output. Now let's talk about generics. Generics is a very important topic of having generic types. It's very useful. Sometimes it's a concept that is not that easy to understand, and usually once you get it in one language you can apply this to different languages. I think the first time that I learned about this it was with Java. Let's say that we want a generic function that takes an argument of any type. Okay, let's say that we want to print it, for example, something like that. So we don't know at compile time the type of parameter that we will have. In this case, we can write a function that has as an argument this type, hence the capital T. T here stands for type. Let's see an example. Let's say we have this struct A, struct single A, and then we have this struct single gen of type T, of generic type T. Here we have single, which is a concrete and explicitly takes of A. You might have a char here, so we can have a single gen of A, or we can have a single gen of 6, or single gen of this character A. Generics are a way to handle functions or other constructs when we want to handle different types. The same rules for structs can be applied to functions. We saw an example with structs. I think examples with functions are easier to understand. They'll have different type of parameters. And using generic functions sometimes requires to specifically define some type parameters. And for example, even the return type might be a generic, or maybe the compiler doesn't have enough information to decide which is the type of the parameter. So in this case, we need to use a generic. Here there are some examples. Let's take this one. We are defining here a function generic that takes an argument s of type sgen t, because sgen t is already using this t, which is the type of the generic, and this function is generic over the type t, like this one. For example, this one implicitly specify the type parameter char to generic. Here we are specifying a type char to this generic function. Once we get used to this, they are very powerful because they allow us to handle different types for functions. This can also be done for implementation, so using the impl keyword, impl t generic val t. Let's say that we have a struct, for example val or generic val t, check this one, and then we implement gen val for this generic type t. So this is the implementation of this one. And when we have this function main, we can have gen val, and then here we can specify a type. We have 3 and 3 I32. But this also works with true. If we try this with a boolean, we get an error on the first one. Instead, the second one works with generics, so with any type. Traits can also be generic. We can define one that re-implements the drop trait. For example, here we have a trait generic over t, which defines a method on the color type, which takes a single parameter t and can have double drop. We can have also multiple generics. Usually, the convention is having t and then u, any letter would work. And in this case, for example, we have empty and null, and we can deallocate empty and null by using, for example, this double drop function. Whatever will pass here will be dropped. There is no output for this, but okay. Bounds. When we work with generics, the type of the parameters usually uses a trait to bound and stimulate some sort of contract that has to be implemented. Here we have a function printer that uses the trait display that we used at the beginning of this bootcamp, and so it requires t. To be bound to display, t must implement display. So we can define this function printer that takes this generic type, which must implement the trait display. Bounding restricts the generic to types that conform to the bounds, like this. Generic instances are allowed to access the methods of traits specified in the bounds. For example, here, the generic t must implement debug. Regardless of the type, this will work properly. And in this case, t must implement has area. We can also use the where clause to apply some bounds in some cases to basically diversify the output. Let's do a test case with empty bounds. Even if a trait doesn't include any functionality, you can still use it as a bound. We have eq and copy that are some examples of this from the standard library. We have for this unit structs, a couple of traits, functions that are only valid for types that implement these traits. And we can define some variables, cardinal, blue jay, and turkey. And since we wrote impl red for cardinal and impl blue for blue jay, red won't work on a blue jay or vice versa, but we can have something like this. So this is also to define this specific behavior. Very powerful. Especially to avoid errors. Can we have multiple bounds for a single type? Yes, they are defined using a plus, like this. We're going into a more advanced concept, but it's here. Let's say that we want this with debug and display. In this case, we have a plus here. Of course, they need to implement the same generic type here and here. Or you can have different generics. For example, we can have t and u. And in this case, we don't have the plus. Let's run it. And we can have debug and display for words. It's shown in a different way. I mentioned the where clause. We can use it immediately before the opening curly bracket. Like this. Here we have this impl with ad, different generics with my trait with a and d for this type, and then we can have this where clause, which is more expressive than using a normal syntax. You can have this one and this one, they have the same output. I think this one is better. We are explicitly telling which is the clause. We also use it here. The new type gives compile time guarantees that the right type of value is supplied to a specific program. For example, age verification function. We have here a couple of structs and impl for years and days. To obtain this new type's value as the base type, you can use the tuple or the structuring syntax like this. You might also hear about associated items that refer to set of rules to items of different types. It's basically just a simpler way to use traits and generics. Let's see a problem. We have a trait that is generic over its container type and has some specific requirements, some traits that the user must specify. Because contains is generic, we are forced to explicitly state all the generic types for f and difference. But to be honest, we just want to express that A and B are determined by C, which is the input. Let's see how we can solve this problem. Container contains 3 and 10, true. First number 3, last number 10, the difference is 7. We can use associated types to improve all the readability of the code, moving inner types locally into a trait. So like this, trait contains type A, type B. The functions that use the trait contains, they are no longer required to express A and B. Without using these associated types, we should have F and difference, A, B, and C, which is the input. And using associated types, we can just type difference C contains, which is a great plus. We can rewrite the previous example like this. I think this is way more readable, especially this function, the difference one. The output is the same, is just the way we write this code. Phantom type parameters. A phantom type parameter is one that doesn't show up at runtime, but it's checked statically only and just at compile time. Sometimes data types can use an extra generic type just for the definition that will be used at compile time, and this has no effect on the runtime behavior. Let's see an example. We use standard library marker phantom data, and we have a phantom tuple struct which is generic over A with another hidden parameter, like this. A phantom type struct which is generic over A with a hidden parameter B, and in the function main, F32 and F64 are called hidden parameters. We have this phantom tuple type specified in this way, char and F32, like this one, phantom tuple, char F32. With, for example, Q and phantom data. We can have a type specified as char F32, like this, struct1, and also this one, struct2. Let's run this one. We have no output, okay. But if we try to uncomment this one, we should get an error. Expected phantom tuple char F32, but we found phantom tuple char F64. Let's see a test case for unit clarification. And let's implement the add trait with a phantom type parameter. We have public trait add with a type output, and here is the whole implementation of this problem. We are using different attributes here, Derive, Debug, Clone, and Copy. For inch and we have the length struct, and then we have this add trait that defines the behavior of what the plus does. And here in the function main, we specify a foot to have a phantom type parameter inch, and you can make a conversion between foot, inch, and millimeters. Let's see it in action, and you see we can have this custom implementation of add, for example, for different measure methods, for example feet and meters. Scoping rules. Scopes are very important. We introduced them and you should already have a concept of what a scope is. Related to Rust, of course, they are very important for ownership, borrowing, and lifetimes. So let's see some examples and how we can use these scoping rules effectively. RAII. Variables in Rust do more than just hold data in the stack. They also own resources. For example, this is box T is a smart pointer that forces to allocate on the heap. memory. Rust enforces this RAII, resource acquisition is initialization. An object goes out of scope, its destructor is called, and its own resources are freed. And this is the logic on how Rust works. And this is of course to avoid resource leak bugs. Our goal is always to avoid bugs. We have an example here with the box smart pointer. We have a function to create the box. Let box1 equal box new. This allocates an integer on the heap rather than the stack. This is what the smart pointer does. At the end of the scope, so here scope is between these curly brackets, box1 gets destroyed and memory gets freed. In this function main, we allocate another box on the heap using the box smart pointer, and then we have a nested scope. This inside this other outer scope. And then we allocate an integer on the heap with a box 3 inside this nested scope, and at the end of this scope, box 3 gets destroyed, and here, just for fun, it creates 1,000 boxes. Then of course it gets destroyed here at the end of this scope. Here is also double checking errors using this valgrind to check if we have memory leaks, and indeed we don't have them. Let's talk about the concept of destructure. The notion of a destructor in Rust is provided using this trait, the drop trait. You can check the documentation. The destructor is called when a resource goes out of scope. And the cool thing is that we don't have to implement this trait for every type. Rust does many of these things automatically. Of course, if we want a specific behavior, we can implement, or at least understand more about it here, for example. And here there is an example on how the drop trait works. When the variable in the main function goes out of scope, the custom destructor will be invoked. Ownership and moves. In this bootcamp we already introduced some terms that might be a bit strange. In this section we will talk about ownership and moves with examples. In Rust, variables are in charge of freeing their own resources, but resources can have only one owner. And why this? Because this prevents resources from being freed more than once or in a wrong way. For example, when we do an assignment or we pass a function by value, the ownership of the resources is transferred. This is how Rust does work, and in Rust speak this is known as a move, because we move ownership. There is also a keyword called move. We will see probably this later. This is an important concept. After moving resources, the previous owner can no longer be used, and this is to avoid dangling pointers. Let's see this example. We have a function with this box argument, smart pointer to allocate on the heap, and then it just prints what is inside this box. And then of course the memory gets freed. In the main function we create this unsigned integer like this, let x equal 5u32, then we copy x into this y variable, we print them like this, and then we declare a variable called a using this box smart pointer, and then we print it. If we type let b equal a, so this box that allocates the memory on the heap, and we try to print a after this line, we will get an error. This function takes ownership of the heap allocated memory from B, this destroy box function here. If we run it, leaving the comments, we have the correct behavior. If we try to uncomment that line, we should get an error, and we have indeed an error. Mutability. Mutability of data can be changed when ownership is transferred. For example, we have this immutable box like this. If we try to mutate this, we will have an error. But for example, we can move the box, changing the ownership and the mutability. So we can type let mute and then mutable box equal to immutable box. This is allowed. Then we can have a print ln of this mutable box, and we can even modify the content of the box like this. This is the reference symbol. Partial moves. When we do a destructuring of a single variable by move or by reference, there are some pattern bindings that can be used at the same time. Doing this will result in a partial move of the variable. This does mean that parts of the variable will be moved and other parts will stay. Note that types that implement the drop trait cannot be partially moved from. Let's see this with an example. We have this function main with a struct with the Derive debug attribute, and we cannot move out of a type that implements the drop trait like this. This is commented. Here we define a new person with a string and a box U8 age, and in this case name is moved out of the person, but age is referenced. We can print the age, we can print the name. If we try to print the person struct here, we will have an error. Person can't be used, but we can use, for example, personal age because it's not moved. Let's try it out, and indeed this does work. If you try to uncomment some of these lines, let's try it out, we should get an error, okay? And why all these box smart pointers? Because in this example we store the age variable on the heap to use this partial move. And if we try to remove this ref keyword, we will get an error on the age here. Let's see an example of a very important concept in Rust, which is borrowing. Usually most of the times we want to just access the data without taking ownership of it. Think when we just want to have a function and do some operations with a variable. To accomplish this, Rust uses something called borrowing. Instead of passing objects by value, we can pass objects by reference, and we will see this ampersand. This is the symbol for passing by reference. The compiler has something called borrow checker that guarantees that all the references will always point to some valid object. Why? Because it wants to be sure that while references to an object exist, the object is not destroyed. For example, there is this function hitbox i32 that just do a print and then it destroys the object. And this function instead borrows an i32. The difference here is here we don't have the ampersand, here we have the ampersand. So we are getting just a reference instead of getting ownership on the argument. In this function main, we create an i32 on the heap using the box smart pointer and i32 integer that by default is allocated on the stack. And for example, we can call this function borrow i32 with some references both to this boxed i32 and staked i32. Inside an inner scope here, we take a reference to the data contained inside the box, and in this case we will get an error because it can destroy boxed i32 while the inner value is borrowed. So the compiler will guarantee that if this is needed, it will not be destroyed. If we try to borrow this ref to i32 after inner value is destroyed, this is possible, and then ref to i32 goes out of scope and then it's no longer borrowed. On this last line, boxed i32 can now give up ownership to this hitbox i32 and it can be finally destroyed. Let's try to run this example. As you can see, we have an error here. We can fix it by commenting this line. Let's talk about mutability. Mutable data can be mutably borrowed using the @mute keyword. This is called mutable reference. Let's see an example. We have a struct of a book here, a function to borrow a book that takes a reference to a book. Check this out here. Then we have a function for a new edition that takes a mutable reference to a book. book, and in this function main we create an immutable book, immutabook. Then we create a mutable copy of that book. This is allowed, we saw this a couple of minutes ago. Then we can immutably borrow an immutable object. This does make sense. We can immutably borrow a mutable object too. We can borrow a mutable object as mutable, new edition, which takes an immutable reference of this, but we can't borrow an immutable object as mutable. This will return an error. See? If we comment this out, we don't have this error anymore. Aliasing. Data can be immutably borrowed any number of times, but while we do this immutable borrowing, the original data can't be mutably borrowed, and only one mutable borrow is allowed at the same time. Let's see an example. We have a struct here of a point, a function main, we define a mutable point here, and we create two references to the point, one borrowed and another borrow. We can access the data via the references. Like this. Println point has coordinates. We can have borrowed point x, another borrow y, and z. But we can't borrow point as mutable because it's currently borrowed as immutable. Would return an error. We can show that the borrowed values can be used again here. If these immutable references are not used anymore for the rest of the code, is it possible to borrow them again with a mutable reference? We can also change the data using a mutable reference. We can't borrow something as immutable if it's currently borrowed as mutable. So for example, in this case, we can type let y equal $point.y. This will return an error. The immutable references can be passed as immutable to println, like this, mutable borrow x, y, and z. Since the mutable references are no longer used for the rest of the code, is it possible to reborrow them, borrow them again? So let new borrowed point equal at point. And then we can print it. Let's try it out, and we have indeed a correct output. Let's talk about the ref pattern. This ref keyword can be used to take references to the fields of a struct or a tuple. Let's see this in action. We have a struct point again. We define a variable c equal to the char q. A ref borrow on the left side of an assignment is the same to an ampersand borrow on the right side. Usually we will see probably this syntax more than this one. We can define a point here, and ref is also valid when we are destructuring a struct. For example, here we have a copy of x, and here ref to x is a reference to the x field of the point. Let point, we have x, ref to x, and then y we don't need it. This equal to a point. We are destructuring here. And then we can even return a copy of the x field of a point with this dereference symbol to ref to x. We can also have a mutable copy of point like this one. And ref can also be paired with the mute keyword to take mutable references like this one. So we can also have ref mute here. Ref mute, mute ref to y, for example, in this case. And we can mutate the y field of mutable point using a mutable reference. Here we have a couple of prints, and as a final example we have a mutable tuple that includes a pointer. This is a smart pointer box, and then we can, inside this inner scope, destructure this mutable tuple, for example, to change the value of this one. Let underscore, we are not interested into this, ref mute last equal mutable tuple. Using the dereference we can assign this value to. This is using the suffix syntax. Let's try it out. Here it is. Lifetimes. Probably understanding lifetimes in a single example is challenging, but let's try. What is a lifetime? A lifetime is a construct the compiler uses to ensure all the borrows are valid. We want that a variable lifetime begins when it's created and ends when it's destroyed. Sometimes this is not obvious because there are also other references, borrows, sometimes things that get more complicated. And it's important to understand that lifetimes are not scopes, even if usually they are explained together in the same chapter. Let's say that we want to borrow a variable using the ampersand symbol. The borrow has a lifetime that is determined by where it is declared. The borrow is valid as long as it ends before the lender is destroyed. However, the scope of the borrow is determined by where the reference is used. And let's see how lifetimes are connected to the concept of scope, but they are different. Here we have this function main. Check this on the right. So when we declare this variable let I equal 3, it starts the lifetimes of I until here. Then we have an inner scope with a borrow lifetime at I. Here we end the borrow of borrow 1. Then inside another inner scope at the same level of the first one, here we can have borrow 2 ampersand I, and here it ends. As you can see here, I, this one, has the longest lifetime because its scope encloses the borrow 1, this one, and the borrow 2, this one. What is important to understand is that the duration of borrow 1 and borrow 2 are irrelevant to each other, because they are at the same level, but they are disjoint. They are not connected from a logical point of view. Explicit annotation. The borrow checker uses explicit lifetime annotations to determine how long references should be valid. If we want to use the explicit annotation for lifetimes, we should use this one with the apostrophe. When we use lifetimes, we need to use generics. This lifetime syntax indicates that the lifetime of something may not exceed that of apostrophe A. If we have multiple lifetimes, the syntax will be this one. Foo has lifetime parameters A and B. In this case, the lifetime of foo cannot exceed either A or B. Let's see an example. For explicit lifetime annotation, we have these printfs with A and B that takes as arguments X and Y. These two lifetimes must be both at least as long as the function printfs. Then we can have a function without arguments but that has a lifetime A. Here we define a variable called X, and if we try to define another variable, let Y ampersand A I32 equal ampersand X, we will have an error. X does not live long enough. Attempting to use the lifetime A as an explicit type annotation inside this function will fail, because this lifetime ampersand X is shorter than Y. In this function main, we can create variables here with a tuple. We can borrow both variables and pass them into the function, and the failed borrow function here contains no reference to force A to be longer than the lifetime of the function, but A is longer. Let's try it out. Indeed, we have an error here. I think that we should do this. Okay, so this is not allowed. We will get an error. Functions. Any reference must have an annotated lifetime, and any reference being returned must have the same lifetime as an input or be static. Let's see an example here. We have this function print1 with a lifetime of A, and as an argument X, which is an I32. We have a function to add 1. This is just to demonstrate that immutable references are possible with lifetimes. You see here this mute keyword with the lifetimes, and multiple elements with different lifetimes can also be done. In this case, we have print multi with A and B, so different lifetimes, and then we have X with A and Y with B. And we can also return references that have been passed, like this one. As an input x a and underscore b, we can return an i32 with the lifetime of a. This is a quick example. Function main, let x and let y. We print 1 and print multi. This is x and this is y. Z equal pass x. You're using this function, and then we print it again, and then let mute t, and we can call this add one with at mute t. Let's try it out, and here is the output. A quick note is that methods are annotated similar to functions, so if we have a struct with some methods, like this one, in the implementation of this owner, you can have this add one with a lifetime a, and in the function main, we can define a let mute owner, and then we can call the methods owner add one and owner print. Structs and lifetimes. Annotation of lifetimes in structs are also similar to functions. For example, we have a struct borrowed a i32. This is a unit-like struct. It can also be used in a C-like struct here. You can also use lifetimes in enums, like this here. And here there is an example in a function main that uses all of these. Let's try it out. Okay, traits and lifetimes. Annotations of lifetimes in traits methods are similar to functions. The impl can also have annotation of lifetimes. For example, here we have a struct with annotation of lifetimes, and we can also annotate lifetimes to impl here and here. Bounds. Just like generic types can be bounded, lifetimes use also bounds. Let's check the syntax. If we have t colon apostrophe a, all references in t must outlive this lifetime a. And if we have t colon trait plus apostrophe a, the type t must implement the trait, and all references in t must outlive a. Let's see this example. We have this trait to bound with. We have this struct ref, and then we can have a generic function that prints the debug trait, like this, with this where keyword. We talked about this earlier. And here a reference to t is taken where t implements debug, and all the references in t outlive a here. In the function main, we define x and ref x, which is a reference to this x variable, and then we print them. Like this. Coercion. A longer lifetime can be coerced into a shorter one so that it works inside a scope that would not normally work in. For example, here, Rust enforces a lifetime that is as short as possible. These two references are coerced to that lifetime. In this second function, with a colon b, it can be read as lifetime a is at least as long as b. Here we take an ampersand a i32 and we return a b i32 as a result. In this function main, we define this first equal 2, then we have an inner scope with second equal 3, and then we can print this multiply and choose first inside this inner scope. Static. Rust has some reserved lifetime names, and one of them is static. I think we already saw this syntax, maybe at the beginning of the video. We can have a reference with static lifetime, like this one, and we can also have static as part of a trait bound. Let's see the subtle difference. A reference lifetime, here static indicates that the data pointed by the reference lives for the remaining lifetime of the running program. Two common ways to make a variable with static lifetime are to make the constant with the static declaration, or to make a string literal which has as a type $static str. Let's see this example. We have a static num, and we can return a reference to num where its static lifetime is coerced to that of the input argument, like this. In this function main, we can make a string literal and print it, like this here. And then when it goes out of scope, this reference of course can't be used anymore. The data remains in the binary, but it's not a big issue. In this case, we make an integer to use for this coerce static, and then we can coerce this num variable to the lifetime of this lifetime num, like this, coerce static at lifetime num. And then we can print it. And then we do a print outside these two inner scopes. Static references only need to be valid for the remainder of a program's life. Here, for example, we use box leak to create some static references, like this here. In this case, it doesn't live for the whole duration, but only from the leaking point onward. Trait bound. As a trait bound, it means that type does not contain any non-static references. For example, the receiver can hold on the type for as long as they want, and it will never become invalid until they drop it. Any owned data always passes a static lifetime bound, but a reference to that owned data generally does not. We have here this function with this input debug plus static, and in the function main we use it. We define this I and then we print it. In this case we have an error because $y only has the lifetime defined by the scope of main. It's not static. Elision. Some lifetime patterns are very overwhelming. We can agree on that. The syntax is not the best. So sometimes we can omit them to save some typing and also to improve the readability of our code. Elision exists in Rust because we have been writing Rust for some time, and so we got used that there are some patterns that we don't want to repeat. I think that in some early versions of Rust, Elision was not there, so the code all looked like this. For example, here this elided input and annotated input, they are basically the same function, but check the first one and the second one, and I think we can agree that the first one is more readable compared to the second one. So this is a common pattern. Rust allowed us to write this, but the compiler under the hood still has something like this. For example, this elided pass and annotated pass, they have an identical signature, but check line 13 and 15. I think we can all agree that line 13 is more readable for humans. And here we have this example. Let's try it out. Okay, so this is basically just syntactic sugar. Okay, we already talked about traits, but this section is dedicated to traits. What is a trait? A trait is a collection of methods defined for an unknown type. Is a sort of contract. If you come from the Java world or other programming languages, if you see trait, you can read them as interfaces. But honestly, I really love the term trait. The term interface took longer to click, I would say, even if they're not exactly the same. Traits can be implemented for any data type. In this example, we define the classic animal and then a group of methods. For example, we can have the animal trait for the sheep data type, allowing it to use the methods from animal when we have a sheep. So we have this struct sheep, and then we have the trait animal. Animal can be created, it has a name, can make some noise, then can sort of talk. Okay, and for example, for this struct sheep, we can also have some specific methods, like shear and isnaked. And if we have a trait animal for sheep, we need to implement the animal trait for the sheep. So we can basically add some specific logic, for example, the noise it does, if it's naked or not, to make an example. And we can also override the trait methods, having this fn talk inside this implementation, for example. And here we can create a mutable sheep dolly and try these methods. Let's try it out. There we go. Derive. The compiler is capable of providing basic implementation for some traits using this derive attribute. We already saw this multiple times. Here is a list of some derivable traits: comparisons, clone, copy, hash, default, and debug. Here we have some examples. But again, the compiler can provide sometimes a basic implementation for some traits. Classic example is the derive debug, so this can be, for example, printed in some ways. We have some examples here. Let's try it out. 1 foot equals 12 inches. 1 foot is smaller than 1 meter. Returning traits with dyn. The Rust compiler needs to know how much space every function's return type requires. This is why we need to specify the type when we have a return one for functions. All the functions must have a return and concrete type. For some other languages, for example, this is not a must. If you have a trait, for example, the animal one we just saw some minutes ago, you can write a function that returns an animal because its different implementation will need a different amount of memory. Is there a workaround for this? Yes. For example, we can return a box that contains some animal. We already saw this box multiple times, but here we have again another definition. Is a reference to a memory in the heap. It's a smart pointer. And since a reference has a statically known size and the compiler can guarantee it points to a heap allocated animal, we can return a trait from our function. For example, we can use this with the keyword box dyn animal. I think it's pronounced dyn. So we can have a sheep and a cow. We have a trait animal. We can implement the animal trait for sheep, implement the animal trait for cow, and then we can return some struct that implements animal, but we don't know which one at compile time, like this one. Okay, this is very powerful, a very powerful syntax. And then we have this function main with a random number, so we don't even know at compile time which one it will be. And then we can define a random number like this one, and then we can define an animal based on that random number. This can also be, of course, random generated, and then we can print and make some noise. This was a sheep, I think. Yes. Operator overloading. In Rust, many of the operators can be overloaded using traits. Some operators can be used to accomplish different tasks based on their input arguments. This is possible because operators are syntactic sugar for method calls. For example, the classic plus is an add operator, and this add method is part of the add trait. This is why we can use this plus operator that is probably easier to use instead of using add every single time. We can also check a list of traits that overload operators here on core ops. And here we have an example: ops add bar for foo and for bar. Let's try it out exactly like this and this one. The drop trait. The drop trait has just one method called dropped. This is called automatically when an object goes out of scope at the end of the curly brackets. What is the main use of the drop trait? Is to free resources and memory during the implementation and the execution of the program. We already saw multiple examples of types that implement the drop trait: the box, vector, string, also file and process. We didn't see them so far. The interesting fact is that the drop trait can also be manually implemented for any custom data type. And this example adds a print to a console to the drop function to announce that it has been called. This is not the normal behavior, of course. So we have a struct droppable. We implement drop for droppable, and then inside here we create some instances of this droppable struct. We have some inner scope here, and I'm curious about the output because here we have some println inside the blocks, and you should also be able to read some of this dropping when we execute the program. This is probably useful also for tutorial purpose. I might do this in the next Rust tutorial series. Yes, as you can see here, you can actually see when this has been dropped. Useful. Let's see a more practical example. Here is how the drop trait can be used to, for example, automatically clean up some temporary files no longer needed. We have a struct temp file with a file and a path. We do the implementation of this temp file, and when temp file is dropped, the file will be automatically closed, and then our drop implementation will remove the file, will physically remove the file. This is a drop of the file. As you can see here, can actually remove the file. So not just memory, but also file. Let's try it out. You can try this locally and see if this file gets deleted. Iterators. Iterator trait is used to implement iterators over some collections, for example, arrays. The trait requires just one method to be defined for the next element. This can be defined in an impl block or automatically defined, for example, as in arrays or some ranges. We have different methods. We will see one with this into iter. We have a struct Fibonacci, and we can implement iterator for Fibonacci. Fibonacci is a series where each number is the sum of the two previous ones. We can refer to this type using self item, this one, and here we define the sequence using .cur and .next. Turn type is an option, so it can be sum or none, and we implement this function next. Let current equal self.cur, self.cur equal self.next, self.next equal current plus self.next. And in a Fibonacci sequence there is no end, so this ideally would never end. We have a main function. Now I'm curious to try it out. I iterate through 0.3 in a range. We can take a specific number, we can skip some numbers. Let's try it out. And as you can see, we have some terms of the Fibonacci series here. The impl trait. The impl trait can be used as an argument type or as a return type. Let's see an example for both of two cases. For example, if your function is generic over a specific trait, but you don't mind about the specific type, you can simplify the function declaration using impl trait as the type of the argument. For example, if we have code like this is a parse, for example, for a CSV document, I think, so there is some logic to parse this CSV document. This can be rewritten in this way. We can have this impl here and in the source as an argument type, as we mentioned. Using impl trait as an argument type means that you cannot explicitly state what form of the function you use. If your function returns a type that implements, for example, my trait, you can rewrite its return type as arrow impl my trait. And this is great for the signature and for our eyes. For example, here we have this combine vex explicit return type like this, and check at the return type. It's literally 2 lines long. This is exactly the same what here we just have this impl iterator item equal i32, and here we have the main function. Some Rust types can be written out. For example, every closure has its own unnamed concrete type. Before having this impl trait, we had to allocate on the heap in order to return a closure. Now you can do something like this: fn make other function and then impl fn i32 arrow i32. Let closure equal move x i32 x plus y, and then closure. You can also use the impl trait to return an iterator that uses map or filter closures. And this makes using map and filter way easier. We have these double positives. It return an impl iterator item equal i32. It numbers.iter.filter.map. Clone. When we have to do with resources, the default behavior is always to transfer them during the assignment of the function calls. This is the default behavior in Rust. Sometimes, or I will say often, we need to make a copy of the resource as well. In this case, we have this clone trait. We can use the .clone method defined by this clone trait, to be precise. If we have a unit struct, we can use these attributes, debug, clone, and copy. We can also have a tuple struct like this that implements the clone trait, you see, like this. And here we can instantiate this unit struct. We can copy this unit. In this case, there are no resources to move, of course, because it's a unit struct. And all the units can be used independently. But if we instantiate a pair struct, this one, and then we move pair into this moved pair with this equal operator, in this case, the initial pair would have lost its resources. If we try to uncomment this one, this will have an error. So in this case, we need to clone this moved pair. The resources will be included here. And for example, we can drop the moved original one using std memdrop. And of course, after this moved pair has been dropped, we can't use it anymore, but this is normal. Let's try it out. Okay, let's move on. Supertraits. Rust doesn't have inheritance, but you can define a trait that works as a superset of another trait. So a concept very similar to inheritance. We can have this trait person, and person in this case can be a super trait of a student. If you implement a student, it will require you to impl the person. Trait student colon person. Let's say that we have a trait programmer with a favorite programming language, and if we have a comp sci student, computer science student, this can be a subtrait of both programmer and student. So if we implement the comp sci student, we need to implement both the super traits. So in this case, programmer plus student, and we can have, for example, the Git username. This is very powerful. A type can implement different traits, as we saw 1 minute ago. What if we have two traits that both require the same name for a function? Let's say that many traits have the method called get, but they might have a different return type. We have a good news. Each trait implementation gets its own implementation block. So it will be clear which traits, in this case the get method, is implemented. And what if we want to call these methods? In this case we have to use the fully qualified syntax, so we avoid confusion here. We have this trait username widget, trait age widget, and then we have a struct form with a username and an age. We have implementation for the username widget with a get, and then age widget implementation with a get too, but they return different things. In this function main, if we try just to use get, we will get an error from the compiler. In this case, we need to use all these long, fully qualified name, but it makes sense because here we want to avoid confusion between the get in the age widget and the get in the username widget. The solution might be to have different names, for example, on line 18 and 24. Let's talk about macros. Rust provides this powerful macro system, and we experienced this since our first print ln exclamation mark in our first hello world. Let's dive deeper into these macro rules, which is basically meta programming. Macros are basically parts of code that gets executed. They look like functions, but their name ends with a bang or exclamation mark. Instead of generating a function call, macros are expanded into source code that gets compiled with the rest of the program. They are very, very powerful. Rust macros are expanded into abstract syntax trees. How can you create a macro? Macros are created using these macro rules macro, which is funny. We are using a macro to create macros. Let's create a simple macro to say hello. Macro rules say hello. We have no arguments here, and here we have just some code. And this of course seems trivial, but this is just to get used to the syntax of the macro. Why are macros useful? To don't repeat the same code over and over again, to have some domain specific special syntax for special purpose, and sometimes we want to define an interface that takes a variable number of arguments. We don't have how many arguments we will have. For example, when we use the println, we don't know how many values we will print out. This is a great use case for a macro. Let's see how to define macros. There are three ideas: patterns and designators, overloading, repetition. Designators: the arguments of a macro are prefixed by a $sign and a type annotated with a designator. In this case, we have something like this. Macro rules create function. It takes as an argument of designator ident, like this, and it creates a function named func name. This is the name of the function we want to define. And for example, this converts this ident, and for example, this stringify converts an ident into a string, for example, a number into a string. We can create a function named foo and a function named bar. This is the name of the function. And then we can have macro rules print a result that takes an expression of type expr and prints it as a string along with the result, like this one. In this case, we can have fn main, foo and bar, and then we can print the result 1 u32 plus 1. Recall that blocks are also expressions in Rust. Let's try it out. Call it foo, call it bar, this one and this one. Okay, so everything is a string here. And these are some of the available designators. Overload. Macros can be overloaded to accept a different combination of arguments. It works similar to a match block. So for example here, macro rules, test, arguments, they don't need to be separated by a comma. We can also use this one with a semicolon, left expression and right expression, and then we can do a print, stringify left, stringify right, and then left and right. And each arm must end with a semicolon, like this and this. And in this function main, we can call this test macro with different parameters. Let's try it out. You see, also with different types. Macros can use a syntax which is similar to regular expressions. For example, it can use a plus in the argument list to indicate that an argument may repeat at least once, or an asterisk to indicate that the argument may repeat 0 or more times. In this example, this one, find min, we have this expression here. You see, common plus. Also, in this last case, the semicolon is optional. Let's try it out. 1, 2, 4. This is to find the minimum. As we already said, macros allow writing don't repeat yourself code by factoring out the common part of functions and or test suites. Let's see an example. We have this one that implements and tests the plus equal and asterisk equal and minus equal operators for vector t. We have this assert equal len and also op. Here we can implement this add assign, mul assign and sub assign functions here, and then we can test it out also with this test attribute. Domain-specific languages, known as DSLs. A DSL is a mini-language in a Rust macro. It's valid because the macro system expands into normal Rust constructs, but it really looks like a small language. For example, let's say that I want to define a little calculator API. We can have something like that. Macro rules calculate. We have this eval aexpr. It forces types to be unsigned integers like this, and then we can have this println stringify. And in this function main we can calculate 1 plus 2 even if eval is not a Rust keyword. You can also check more complex interfaces such as lazy static or clap. What is a variadic interface? For example, println can take an arbitrary number of arguments, and we saw this at the beginning of the video. And we can extend our calculate macro from the previous section to be variadic. This is the pattern for a single eval, and we can decompose multiple evals recursively, like this one. And in this case, we can evaluate also with a different amount of arguments, like this one. This is very very powerful. This was just a basic example, but for sure this is very powerful. Let's talk about error handling. Error handling is this process of handling all the possible failures in our program. Example of error is that an HTTP request fails. You can have an error while reading a file because the file is not there, or the file can't be read. There are many different use cases when we interact with databases and so on. There are different ways to deal with errors in Rust. We will try to cover all the examples. The first rule is that an explicit panic word, we saw that some time ago, is useful for test and dealing with unrecoverable errors. We'll talk about recoverable and unrecoverable errors. It can be used to prototype, and also in tests, the panic word is useful because we want something to explicitly fail. We also have the option type that is great when there might be a lack of value. In Rust we don't have the null keyword, we use instead this option keyword, which can have a sum or none value. We will see some basic examples. We will see the unwrap keyword. We will see the expect keyword that also contains an error message. We will see many examples. If the caller has to deal with the problem, then we can also use result. We will make examples, and we can also, of course, still use unwrap and expect, especially at the beginning when we want, just to handle the positive case. I think it's fine to just start with unwrap or expect. Let's start. Panic is the simplest error handling mechanism that prints an error message, start unwinding the stack, and usually it just exits the program with a bad message. So here we are explicitly calling panic in our error condition. Let's try it out. Thread main panicked. This is an intentional panic by us developers, and we have something like this with the Rust backtrace and so on. We can also have different code paths for the panic keyword, and they are abort and unwind. This depends on the behavior we want when our code will panic. We can define this as we see here on line 4, so panic equal abort. We define this panic strategy, and here, for example, we can use panic unwind as a keyword. Let's see what is the different output. You can see it from the browser. The panic strategy can be set from the command line using abort or unwind in this way. Now let's talk about option and unwrap. In the last example we did an introduction to program failure at will, so we decide that the program will fail. A great way to handle this is to use an enum called option that is part of the standard library, and option is useful when the absence of something is a possibility. For example, we get nothing, we get the null string. Option has two values, some t, where t is a generic, or none, that means nothing, no elements was found. It can be used using a match statement, is probably the favorite way, or we can also use it with unwrap. We will see, I think, both of the examples. Let's see here, we have a function give adult a drink, and we can match different options. We have two options with sum. It doesn't have to be just one. For example, we can have a sum with a specific value, or also sum with something else, like this, with different outputs. And we also need to handle the none one. In this case, all the drinks are handled explicitly using the match statement. In this other case, we have this function drink, and we use the unwrap feature. We have an option as an argument type, and inside here we type .unwrap. This is to avoid writing all this match statement. If we have something simple, we can also use this one. Of course, if this will return none, this will also panic. And here we also can add an additional panic case, in case, for example, if inside is lemonade. Let's see this example in action. Thread panicked here. I think it's because we used none here. We can also unpack option with the question mark. You can unpack option using the match statement, but we can also do that with this question mark operator. To be honest, I like this syntax. Next birthday, that has an option in input and an option string as output. And you see we have this one. As you can see, we can have let next age u8 equal current age question mark plus 1. You can also chain many question mark operators together. Combinators map. Match is a valid method for handling options, as we saw, but you can also find it a bit tedious, maybe also a bit verbose, especially when we have operations only valid when we have an input. In this case, we can use something called combinators. Let's see some examples. Option has a built-in method called map, which is a combinator for some simple mapping of some, and known. Let's see this. In this example, this function process here on line 34 replaces all the functions that we wrote previously. So we have here some structs, we have an enum for food, apple, carrot, and potato. We have a struct peeled, struct chopped, and a struct cooked, always for food. We have the function to peel, function to chop, and the function to cook. Instead, we can have a single function to peel, chop, and cook food all in sequence, which is, I think, great. We have this process function, food option, food as argument, and it will return an option cooked food. And as you can see, we have food.map peeled.map peeled f chopped.map chopped cooked. It's basically processing all these functions in order. We also have a function to check if there is food or not before trying to eat it, if it's edible or not. And then we have here a function main. Let's try it out. And yes, it worked. Love cooked apple, love cooked carrot, and here we didn't have anything edible. We talked about the map combinator, but if you use a map, we have a nested option C, and we start chaining all of them. This can become confusing kinda quick. We can also have a combinator called and then. In some languages, this is called flat map. What about this and then combinator? Calls its function input with the wrapped value and returns the result. If the option is known, then it returns known instead. In this case, we have an enum for food and an enum for day, a function to check if we have the ingredients, for example for sushi, and one to check if we have the recipe. To make a dish, we need both the recipe and the ingredients, and we can represent this logic with a chain of match, like this one. Instead of this, we can have something like that, cookable version 2 with a map, or we can have this I think in a more convenient written way, which is using this and then operator. This is especially useful when we have a sequence of operations we want to do and we don't want something nested to each other. For example, for it, we can use a match statement with, for example, this cookable version 3, which is the one with the and then combinator. Let's try it out, and it worked. Unpacking options and defaults. There is more than one way to unpack an option, even if the default is known. For example, we have or. It's also chainable and eagerly evaluates its argument as is shown in this example. Let first available fruit, no fruit, dot or, orange dot or apple. So we can chain this with or. Let's try it out. We have orange in this case, because it tried the orange first and then apple, even if we defined the apple before. We also have the or else, which is chainable and evaluates lazily and keeps empty value intact. Let's see here, or else is used here. We have let get kiwi as a fallback with some fruit kiwi, or let get lemon as fallback, some fruit lemon. And as you can see here, we have let first available fruit equal no fruit dot or else get kiwi or else get lemon. If we try it out, we have this output. We also have get or insert that evaluates eagerly, modifies empty value in place. To make sure an option contains a value, we can use get or insert, like we do here. And this is used in place with a fallback value. As we see in this example, we have this mutable my fruit, which is known, then we have an apple, fruit apple, let first available fruit, my fruit get or insert. If we try it out, we have the apple as a fallback. We also have get or insert with that evaluates things lazily and modifies empty value in place. So instead of explicitly providing a value to fallback, we can pass a closure to get or insert with. Let's see this example. The get or insert it with is used here and here, so like this here, we have this first available fruit equal my fruit dot get or insert with, and then we have this get lemon as a fallback, which is this one that prints providing lemon as a fallback. This is using a closure. If the option has a value, it's left unchanged and the closure is not invoked. So if we already have this apple, in this case we will not insert the lemon instead. Exactly. Result. I think we already saw this a couple of times, which is a more powerful version of the option type because describes some different and possible errors. This is especially useful, I don't know, for HTTP requests and something like that. We have this result TE that can have an OK with the element T found as one of the possible values, or error, which is an error that was found within these elements. And this is useful, for example, especially if we have some specific errors about this specific construct. The default expected value is OK. And the like option result has many methods associated with it, unwrap, and so on. Let's see an example here. In this case, we have a function to multiply a first number and second number passed as strings. And then, of course, we need to parse them using this parse function. But we know that the parse can fail, so we need to unwrap this parse function. Let's try it out. In this case, we have an error, for example, for this t. We can use result type. Usually the main function doesn't have a return type. When we write our first hello world, it looks like this. But in some cases, we can return a result like this from a main function. So the main function is also able to have a return type of result. In that case, if an error occurs in the main function, it will return an error code. We can also have map for result. Let's see an example. First, we need to determine the error type. Let's see this example. We have a match statement on this first number parse i32 that returns a result, and in case is OK, we try to match this second number parse i32. In case it's OK, we return first number, multiply the second number, otherwise an error, otherwise an error. Okay, here we are nesting match statements. Probably it's not the best syntax ever. This is just to have an idea. Also in the function print, we can have a match on this result. This is a very common syntax that we have a result used with a match statement. It's a very nice combo. And in this function main, we can have 20 multiply 10 and 2, and the second example will provide an error. Let's try it out. In this case, you see it handled the error. Also the parse function returns a proper error message, and here we can see invalid digit found in a string. This is probably useful also for debug purpose. Map and then and many other combinators, they already have the implementation for result, so we'll have all the error handled gracefully, as you can see here. Okay. Aliases for result. What if we want to reuse a specific result type many different times? We already talked about aliases, but let's talk about aliases for result. At module level, we can create some aliases that can be particularly helpful. Let's see a quick example. We import this one. We can define a generic alias for a result with this error type parse int error. We can use this type instead of result t parse int error, like this one here. We use directly this type. This is better than writing this very long error based on result. You see the syntax becomes verbose. Let's talk about early returns. In the previous example, we handled the errors using some combinators, map, and then. There is another way, and it is using the early returns. This is exactly what it sounds like. We can stop executing the function and just return the error. As you can see, we don't have the nested matches anymore, but we have them at the same level. Honestly, I prefer this syntax compared to the previous one. And if we try it out, we should still get an error, the error invalid digit found in string. Okay, if I try to type 4 here, we should have correct output. let's talk about the question mark operator, because sometimes we just want to just unwrap, and because there is no possibility to panic. In this case, this question mark operator is almost exactly the same as writing unwrap. Let's see how this can simplify our code. As you can see here, and once we get used, I think it's a valid option. For example, here we have this first number, string parse i32 with a question mark at the end. And also here. Usually, after I get used to my code, I like to use this syntax with a question mark at the end. Let's try it out, and we have the same error. Okay, the code is similar, but we are testing different versions. We have the try exclamation mark macro. This is basically just another version of this question mark. So we can have try before this. Honestly, I prefer the question mark at the end, but we can also have this syntax with this try before this result. And we have the same output. What if we have multiple error types? Sometimes an option needs to interact with a result or result t, error 1, error 2. So how can we handle different error types? Let's see this example. We have this function double first, with this first one that generates error 1 and the second one that generates error 2. Let's see it in action. Thread main panicked called optional wrap on a known value. In this case, vec first returns an option and parse i32 returns a result. How can we pull the results out of options? The most basic way of handling these mixed error types is to embed them one in each other, like this. Let's try in this way. Sometimes we want to stop processing on some type of errors, but we want to keep going. For example, if the option is known, we just want to ignore this. In this case, we can use a useful function called transpose that is very helpful in case we want to swap between result and just option. Okay, keep this in mind. Let's try it out. Okay. Can we define a custom error type? Of course we can. Rust allows us to define our own error types. In general, a good error type represents different errors with the same type, presents nice error messages, and it's easy to compare with other types, like this. It can hold information about the error, like this one, and it also composes well with other type of errors. This is our goal, to have our custom error, but we want to use this along with other errors. For example, here we can define our error types like this, struct double error, and here is the implementation. We have an example here where we use it, you see here, and then we have a function to print the results, and here a main function. Let's see this in action, and we can have this double error. Invalid first item to double. We just created our custom error type. This was very simple, but it was useful. We can also preserve our original errors using the box smart pointer. The standard library usually helps in boxing our errors. Let's see this in this example with this box dine error, like this here. The box implements conversion from any type that implements the error trait into the trait object box error. And this is the example. Other uses of the question mark that was previously explained as either unwrap or return error, it's almost true. It actually means unwrap or return error from error. If you use the question mark where the error is convertible to the return type, it will automatically convert. For example, here, if we use the question mark, here, the map error will go away when from is implemented for our error type. Here and here. Let's try it out. And we have this one. Wrapping errors, an alternative to boxing errors, is also to wrap them in your own error type. So you remember we created our own double error, like this. We can wrap these errors in our own error type that we defined. For example, here we have double error empty vec and parse int error. And we have the implementation fmt display for double error, and for example we can return different error types here. So basically here we implement the conversion from parse int error to our own double error. And when we use this function here, we should see the correct result. In this function main, let's see. And you see, we are using our own custom error that wrapped other error types. Iterating over results. For example, an iter map can fail. For example, let's say that we have a map of a parse function, like here we have tofu, which is clearly not a number, and we'll have an error here. We have an error, and we also can see OK and OK here. So in the result, we also see that we had an error only on the first one. What if we want to ignore the failed items? I think this is a very useful function, because let's say that we have a vector of strings. Some of them are numbers, some of them are not. Maybe we don't want this to return an error, but we want this to fail silently. In this case, we can use this filter map. I like it. We can just have a list of all the parsed numbers here. We can also collect the failed items with map error and filter map, so we can, divide all the errors. Result implements from iterator so that a vector of results can be turned into a result with a vector. And once a result error is found, the iteration will terminate using this collect. In this case, it fails because it was the first one. We can also collect all valid values and failures with partition. We are collecting the OK one. If we want to have the actual numbers, we need to do some extra steps here and unwrap the current result of the OK. Let's talk about the standard library types. So the standard library provides many custom types that expands on the primitive types. We will see some of them in this section. Growable strings, growable vectors, option types, error handling, heap allocated pointers, and so on. You can check all of them, of course, in documentation. Here we will see just the most important ones. Box, stack, and heap. Usually values in Rust are allocated on the stack. Some values can be boxed, it means allocated on the heap, using a box. As we say, the box is a smart pointer that allocates a specific value on the heap. When the box goes out of scope, it calls its destructor and the inner object is destroyed and the memory is freed. The box values can also be dereferenced using the asterisk operator. Let's see an example. Here we have a struct, a rectangle, boxed origin that returns a box point. This allocates the point on the heap and returns a pointer. And in the main function, we have these stack allocated variables, and then we have an heap allocated rectangle because we used this box for the rectangle. Also, the output of functions can be boxed like this. We can also have a box of a box, of course. Let's see the output of this code, and we can read some of them are boxed, some of them are not. Vectors in Rust are resizable arrays. Arrays in Rust have a fixed size, but vectors not. Because a vector is represented by three parameters: the pointer to the data, the length, and the capacity. The capacity is to indicate how much memory is reserved for the vector, and the vector can grow as long as the length is smaller than the whole capacity. When this threshold needs to be surpassed, the vector gets reallocated with a larger capacity. In this function main, we have this collected iterator of type vector of i32 items, from 0 to 10 excluded. We can also use this vec exclamation mark macro, useful to initialize a vector. Usually I use this one to initialize a vector. We can insert a new element at the end of the vector with the push function, but this is only possible on mutable vectors. As you can see here, we have mute. If a vector is immutable, and that's the default, it can't grow or shrink. We have the len method to have the length, of course. We have the indexing using the square brackets, like we have in JavaScript, the pop that removes the last element. This is similar to other programming languages. Out-of-bound indexing that yields, of course, a panic if we have, for example, just 2 elements and we want to address the third one. And vectors can be easily iterated, for example, using a for-in loop. You can also have this syntax, I like it, that we have a for and then the index and the element in this xs iter.enumerate vector. We have this useful itermute function that allows to mutate a mutable vector during the iteration. So we can modify, for example, all the elements in a vector using this itermute. Let's try it out. We have an error here because we need to add on line 3 collected editor, or we can just comment this one. Okay. Let's talk about strings, especially string with capital S and @str. What is the difference? A string is stored as a vector of bytes, vector of U8, but it will always be a UTF-8 sequence and is heap allocated, is allocated on the heap. Instead, an &str is a slice that always points to a valid UTF-8 sequence and can be used just to view and read strings. It's basically a view into this vector, this string. So when we have something like this is a reference to a string allocated in read-only memory. Sometimes we just need that. We just need a string that then we are able to read and not modify. So if we want to modify a string, we need a string with capital S. If we want to have something that we just want to read in our code, we can use a string slice with this &str syntax. And here we have some methods for strings: sort, split, reverse. I will go fast here. If you want, you can check the standard library for all the methods, modules, and so on. Let's talk about literals and escape characters. Generally, special characters are escaped using the backslash, as it is in many other programming languages, so you can use some specific characters to the string without making Rust think that you are actually writing some code. The classic example is the quote, like this. We want to actually put the quote in our string and not as a delimiter of the string that you are actually writing. And if we want a backslash, we can escape it with backslash. So we have a double backslash. There are some ways to escape multiple characters. You can see them here. For example, if we want to escape many characters in our string, you can use these methods. If we want a string that is not an UTF-8, we can use byte strings, like this one. This is probably not a day-to-day use case, but it's important to understand that they exist. The option enum is very useful because it has two variants: none to indicate the failure or lack of value, or some with the value itself. And here we can see an example. We already saw some of them, but here we have an additional example of the option enum. And of course can be pattern matched, very useful combo. So we can have none or some and have different behavior. Okay. Result, we already introduced that, but let's make a recap. Result is very similar to option, but sometimes we want to say why something failed, so maybe we want to return an error. And this is where result comes to the rescue. It has an OK with the value. This is very similar to sum with value, but then it has, instead of none, an R with Y. We can actually explain why this thing failed. And this can also be used with a match or also with an if else statement. Of course, we don't have to use a match statement, even if I am a fan of it. And this error can have different types of errors. For example, here, the specific math error division by 0. And this is because maybe we want to handle this in different ways. We want to return a different message and so on. Let's try it out. Okay, the question mark operator is useful to make things pretty again here. So instead of having a match statement to handle all the possibilities, we can have this question mark, and this makes things a bit more readable. This is just a matter of readability. The panic macro can be used to generate panic and start unwinding the stack. While unwinding, the runtime will take care of freeing all the memory and resource owned by the current thread where this Rust program is actually running. And of course it calls the destructor and drop on all the objects. Let's try it out. We have this error, and you can also use Valgrind to check that this is not leaking memory. Let's talk about hashmap. If vectors store values by an integer index, hashmap stores values by key. It's a key value pair data structure. Hashmaps are growable, but they can also shrink when they have accessed some space. Let's see an example. We can do something like this. I think this example is easier to just understand it. We can define this hashmap new, and then we can have contexts insert that insert basically a name and a number. And there are some methods specific to the hashmap. We have, for example, get. If we want to get the number of Daniel, this returns an option. So this can be sum in case we find a value for the key Daniel, or in case it doesn't find it because maybe we spelled the name wrong or the name doesn't exist in this hashmap, then we can return, for example, an error message. We can insert. Of course, you can check all the methods. So here we are just want to mention that we have the get, insert, remove, and the generic data structure called hashmap. Let's try it out quickly, and we have here the example of the output of this one. Let's talk about alternate custom key types: bool, int, uint, string, and ampersand str. Any type that implements the EQ and hash traits can be a key in the hashmap. So these can all be keys in the hashmap. You can also implement EQ and hash for a custom type. For example, let's say that I want an account. We need to derive partial EQ and hash, and then we can use account as a key in a hash map. And here we have some examples with insert and so on. Let's try. Okay. Hash set is basically a hash map where we just want to care about the keys. Hash set is basically a wrapper around hash map. What's the point of using a hash set where we could just use a vector? A hash set doesn't have duplicates. If you insert a value that is already present in the hash set, then the new value will replace the old one. So this is just to be sure that we will have a set of all unique values. And it has some operations like union, difference, intersection, symmetric difference, and so on. It's very similar to sets in math. It's important to understand that we have this hash set data structure that can come really handy in some situations. So if we go back on ownership, I told that you can have just one owner, and this is still true, but what if we want to have multiple ownerships? So not exactly at the same time, but let's say during the execution of a program. We can use a smart pointer called reference counting, RC for friends, and it keeps track of all the references and all the owners wrapped inside this RC. And the RC, reference counting, increases by 1, hence the counting, when this RC is cloned, and it also decreases by 1 when one cloned RC is dropped. So it really keeps track on how many references and owners are on that specific value. We can create it like this. Of course, we need to import it. We can have this RCA with RC new, and then we can have the strong count of all the references. And of course, it increases every time we clone or add something new. I want to try to test this out. Again, this is just an example, of course, and we can see this increasing. ARC stands for atomically reference counted, and sometimes we need to share ownership between threads. So we're talking about concurrency and parallelism here. This can create a reference pointer for the location of a value in the memory heap while increasing the reference counter, as it shares ownership among threads. RC is for single threads, of course, and ARC is for multiple threads in this case. So for example, here let's see an example. We have this ARC new and this apple, and then we have this for cycle. We clone it. we spawn a thread. This is how you spawn a thread. We also give ownership to the thread. Let's see it in action. We also see this sleep duration, okay? So we can have all the instances printed out. There are many other types provided by the standard library, and we will see some of them in this section. Threads, channels, file input, output, and so on. Let's start with threads. We saw an example a few minutes ago. Rust provides this easy mechanism, I would say, to spawn a native operating system threads using this spawn function. It's really as easy as we can see it here. There it is. Let's try it out, and we can see the number of the thread here. Rust was born for efficiency. Now we will see an example. We will see how easy it is in Rust to parallelize data processing. As we saw, the standard library provides this really easy way to create thread primitives out of the box in a very easy way. Now let's see an example to sum all the digits in a block of numbers. And we'll do this dividing this task into chunks, and each thread will sum just a tiny block, and then we will sum all the intermediate sums of each thread. Let's see this example. We need to import a thread. We have this very long, not really long, but let's say long string of data. We have a map phase when we divide this data into segments like this, and then we spawn a thread to calculate the intermediate sum of each segment. And at the end, we sum the result of all the threads. And here we have the final result that will be basically the reduce phase, when we collect the intermediate result and we combine them inside the final result. And of course, this is just a very quick one. Each thread is doing its job, and then we have this final sum result. Now think about reading a super long list of data. This might come really handy. Of course, when spawn threads, we should be very careful because this can consume all the memory. We should always consider this is a very resource intense consuming activity. What if we want to make communication between threads? Rust provides a very simple way, which is called channels. They allow this unidirectional flow. So there is always a sender and a receiver. You can see them here. They have two endpoints, the sender and the receiver, and we need to implement both of them. They implement a protocol called MPSC, which stands for multiple producer, single consumer, and we need to define both the sender and the receiver. Otherwise, we will have an error. If, for example, if we just define the sender, each thread will send its ID using the channel, and then we push it. Here we define how many threads we want. We will have 3 threads. If we put 5 here, we should be able to see 5 threads. Indeed. Also with the number, of course. It's not in order, of course. It depends. Let's talk about the path struct that represents file paths in this underlying file system. And this is very useful because we know that we have different path structs depending on the operating system. Usually one for the Unix-like systems, including Mac, and one for our beloved Windows. A path can be created from an operating system string and provides some methods to get some information. So we want to abstract this path logic. This will be the dream. So we don't have to deal with different paths depending on the operating system. We have this path new, path display, and then basically we can work with paths, and this can be easily converted to different operating system version. Let's try it out. And we have, for example, this new path. And we have, of course, different methods, some of them for POSIX and some of them for Windows. File input output. This is an important part for each programming language. Let's see how Rust handles input output for files. Of course, something can go wrong with files, and it will. This will return this result. This is handled using, of course, Rust constructs. Failure of all the input-out operations are explicit. Let's see an example. Open function, classic function to open a file, in this case in read-only mode. In this case, the file owns this resource, and the file descriptor takes care of closing the file at the end. We are using a path, including the name of the file, and then we have, you see, this match file open. I really love how Rust handles this, that we have this open and then error y, and OK the file. And for example, here we are reading all the contents of this file inside a single string. In this case, we can insert this hello world string inside the file, and then we can open it with Rust, and it will give the output of what is inside this file. You can try some examples. For example, if the file does not exist, and you will have specific errors related to the input-output. The create function opens a file in write-only mode, and if the file already exists, the old content is destroyed, so be careful when you use this one. Of course, this option can also fail, the hard drive is full or for other reasons. In this case, we will get a specific error, otherwise the file will be created and we will write this content in this file. Again, be careful, because if the file already exists, the old content will be destroyed. A classic way we want to read a file line by line, this is a classic use case. This is probably most famous than reading the whole content in a single string and then probably parse everything. We want to read this file line by line. We can have this way function read lines with a for loop, for line in read to string file name.unwrap.lines, and then we push it. So this is a way. Lines returns an iterator. We can also perform a map in line and collect all the results. You can use this syntax. I prefer this one probably. Child processes. The process output struct represents the output of a finished child process, and the process command is the process builder. For example, here we have this output command new Rust C with the version, with the arguments, and then we have an if-else statement. So if the output status is success, we have this one, otherwise Rust C failed, and we have this on the standard error. This process child struct represents this child process and exposes a standard in and standard output and standard error handles to interact with this process. For example, here we can spawn this wc command new wc, and we can have this process that uses a match statement on this. And in case of OK, it processes, otherwise it panics. We can write a string to the standard input of WC, like this, and of course we'll return an error in case. And because the standard input does not leave after the above call, it is dropped and the pipe is closed. The standard output field has the type option childs as standard output, and so it must be unwrapped here. And again, we are using a match statement for OK and error. If you want to wait for a process child to finish, you must call child wait function, which will return a process exit status. We want to be sure that the command process will wait for the child one. The stdfs module contains many functions to have to do with file system. I'll go quick here, but you can check all the functions in the documentation. For example, to create a directory, we have create dir, create multiple directories, create a symbolic link. All the functionalities of an operating system can be done using this fs module. This is just to have an idea that you can do rm, rmdir, read, cut, and so on. Good luck with reading all of these. I suggest to do this, of course, when you need them. Program arguments, also called environment variables. The command line arguments can be accessed using this std-env-args that returns an iterator that wields a string for each argument. And it's important to mention that the args0 is used to call the program, and all the arguments are passed as command line parameters. For example, here I have 3 arguments, 1, 2, and 3. There are many crates that provide this extra functionality. One of them, probably the most famous one, is clap, to parsing CLI arguments. Of course, we can use the match statement to parse some simple arguments. For example, here, depending on the output, we want to execute a different code, and here we can execute our program using these arguments. A very interesting aspect of Rust is that it provides foreign function interface, also called FFI. Rust provides this FFI two C libraries. This means that you can use C code inside Rust code. This is a very powerful and advanced feature. I think this is just worth mentioning because this would require probably a whole separate video or series. So if you want, you can get used with this FFI using this example, and it uses this extern keyword. My goal here is just to mention that we have this interface to an external library, in this case C library. Let's talk about testing in Rust. Unit testing, test our Rust function to verify the non-test code is functioning in the expected way. Let's make just a quick introduction here. Tests can fail. Sometimes we want to test the behavior when the code panics. We have some simple feature like assert and assert equal, and usually we add this attribute CFG test, and we have a specific module. Something I really like about tests is that they can all be run using cargo test. Starting from 2018, your unit test can return a result, which makes the Rust developer really happy. So we can use this question mark. As I mentioned, we can also test panics, like this, should panic, expected. So you can also test the panic behavior in the code. And this is the output that we should have in this previous example. We can run a specific test, for example, a specific function, or we can even run multiple tests on some specific parts. I really like the fine-grained level of control you have when you run tests. You can also add some tests to be ignored using this ignore attribute, or we can also run just the ignore test. We have here the output of the test ignoring the one that has the ignore, or we can run the ignored ones. A very important part when we have to do with documentation is that we need to do documentation testing. Here there is this section about common markdown specification. Rust really takes care of everything to be correct. We are using this 3/ symbol to indicate documentation. This is an example. Probably if you want to publish a crate on crates.io, you need to make all this documentation. And the main purpose of documentation test is to serve as example, so who will use them will know what to do. Unit tests are important, but integration testing is important too, as maybe we want to test the behavior of a whole module. Cargo looks for integration tests in this tests directory, which is close to the src1. We can run them using cargo test. And it's important to notice that each Rust source file in the test directory is compiled in a separate crate. If we want, we can import it, but by default they are separate. Creating the module as test.common.rs also works, but is probably not recommended in this case, because maybe we want to run them as a separate crate. Dependencies. Sometimes, or maybe always, we need to have some dependencies for test. For example, for benchmarks. We can add some specific dev-dependencies only here in the cargo.toml file. For example, let's say that we want these pretty assertions, which just extends this assert and assert ne function to have some, for example, different colors. So this is not needed in production, but just for us as a developer. Remember that we can add these crates in this dev dependencies section in the cargo.toml file. Unsafe operation. This is a section that probably would need a separate whole video, and maybe we want to minimize the amount of unsafe code in a code base, but I like the idea that Rust gives us full power and full functionality, if we know what we are doing. Let's make a very quick introduction. We can have row pointers. Very dangerous, but we can have them. Row pointers and references. The difference is that references are always safe, but row pointers are not. And the referencing a row pointer can only be done if we have an unsafe block. So tell Rust, hey, here I know what I'm doing, just let me do my own stuff. We're basically removing all the safety belts. We can then have a more, let's say, C-like behavior. I like this a lot, that we can unlock all the power. The functions can also be declared as unsafe, so it's the programmer's responsibility to ensure all the correctness of this one. one. We have an example here, which will create a slice given a pointer. This would be dangerous, but of course we can have this in this unsafe code. Rust provides support for inline assembly using the ASM macro. This can be used, of course, for embedded unwritten assembly in the assembly output. So this is very interesting. This is just a simple basic usage, I would say a hello world of this ASM macro. It's very fascinating. For example, here we can insert an instruction here with this mov. I'll go quick here because basically here we are testing some assembly functionality. This is important, just this. So ASM, move, add, out, in, and here we have more and more examples. You can check this part. You can specify different variables for the input and output, like this. We can have late output operands like this. This has to be inside an unsafe block, and then we can use variables that are here. And again, there are many examples here. Explicit register operands like this. We can mess up with the registers, the mul instruction. Maybe this is more interesting for someone who is more focused on assembly, but it's important to understand that we can actually do this in Rust using this macro. Global the registers. I did that during my computer science degree. Here we have push, CPU ID, move, pop. We have all the assembly instructions. I'll go quick here. Symbol, operands, and ABI clobbers. Here we can check this one. This will require a different and separate video. Register template modifiers, memory address operands, labels. We have basically full functionality here and compatibility with assembly. Options. I will leave a link as a reference to all of these inline assembly. This is not the goal of this one. Compatibility. The Rust language is evolving very quickly, and because of this, some compatibility issues can arise, despite, of course, the efforts of the Rust team to have a full complete compatibility. And there is a link here to the raw identifiers. To conclude this complete Rust bootcamp by example, there are some topics that probably you want to dive deeper. The one step is to check the documentation here. One step is to check this playground. There is an online book. And one good news, if you want to dive deeper into Rust, is that I have a whole full Rust course based on all the lessons on the official Rust book. Basically, what I'm doing is that I'm go here. It looks similar, but it's not what we did today. And all these lessons, they are in video format on this channel. I will leave a link below. For example, if you want to know more about ownership or about the RC counter or about the closures, I made single lessons. This is probably a good place to go if you want to dive deep into specific topics. And I also add some theory lessons. They are quick, no worries, but just to give some ideas before we dive deep into code. In this case, we just jumped into the code because this is the idea of this video. Learning Rust by example. If you have any question, just drop them below. Congratulations, because you finished this very long video. I would like to have your feedback. If you want me to create videos on other specific parts, or maybe longer videos, or maybe we'll make a part 2, or we can make an improved version of this one. Maybe in the next one I will do this with my own examples. And I also see that there is some repetition here, so maybe we can make it a bit smoother. What I would like to do is that I don't want to introduce concepts like the match statement, option, the box, smart pointer without even introducing them. Maybe I will do something like that in the future. For now, thank you so much for watching. If you want, just leave a like and leave a comment. Best of luck in your developer journey to learn Rust, and see you in the next one. Bye bye.